One thing in our galaxy keeps NASA up at night. A star that is so thick and unstable that it is watched 24 hours a day, 7 days a week. Even though it's not the biggest, best, or most well-known, it's the one that's most likely to fall apart without notice. A neutron star called PSR J0952-0607 is shown here. It spins faster than a jet engine and is almost about to fall apart. Every heartbeat we see could be its last. If it gives up, it won't just fade away. It will turn into a new black hole. Because of this, NASA keeps an eye on it 24 hours a day, 7 days a week. When it finally falls over, the whole world will blink. Unstable by design, the cold open. NASA keeps an eye on one star in our sky all the time for a reason. It's not the biggest star in the Milky Way or the most beautiful cloud that can be seen through a telescope. It's not big, barely the size of a city, and most people can't see it. Still, somewhere in the northern sky, past the constellation Sextans, something is spinning faster than any machine ever made by humans. Every turn is a scream of radiation that is so accurate that you could set your watch to it. But underneath that perfect beat lies chaos. It looks like the star is about to destroy itself. If you add a tiny bit more mass and a breath more pressure, it will cross the line that physics itself set, and it will collapse into a black hole. So NASA keeps an eye on it all the time. It could be a cosmic clock 1 second and not be there the next. What they're watching is what astronomers call a millisecond pulsar, a neutron star rotating hundreds of times each second. The Black Widow pulsar, its unofficial nickname borrowed from the deadly spider that devours its mate, is the fastest of them all. Picture an object only 20 kilometers wide, spinning 700 times per second. Its equator moves at a significant fraction of light speed, yet it somehow holds together. Gravity crushes it inward with such ferocity that atoms no longer exist. Protons and electrons fuse into neutrons, packed tighter than anything outside a black hole. A teaspoon of this matter would outweigh a mountain chain. On Earth, it would fall straight through the crust and settle in the planet's core. To understand why it's unstable, you have to understand what keeps it alive in the first place. When a massive star runs out of nuclear fuel, its outer layers explode in a supernova while the core collapses. What's left is a neutron star, matter so dense that it balances on the knife edge between gravity and quantum physics. The only thing stopping it from total collapse is neutron degeneracy pressure, a quantum rule saying no two neutrons can occupy the same state. That microscopic defiance holds up an entire star. But there's a limit. Theoretical calculations, called the Tolman-Oppenheimer-Volkoff limit, suggest that once a neutron star exceeds about 2.5 to 3 solar masses, that pressure fails, gravity wins, the star implodes, forming a black hole. The Black Widow pulsar sits dangerously close to that threshold, about 2.35 solar masses packed into a sphere smaller than Manhattan. How did it get there? By feeding. This pulsar isn't isolated. It orbits a faint dying companion star only a few million kilometers away. Over millions of years, its gravity has been stripping that neighbor bare, pulling streams of gas into a swirling accretion disk. The material funnels down magnetic field lines and slams onto the neutron star surface, heating it to billions of degrees and spinning it even faster. Each stolen atom adds angular momentum, like an ice skater pulling their arms in, and with every turn, the pulsar creeps closer to disaster. Hence the nickname, it's eating its partner alive. The balance it keeps is incredibly delicate. It's kind of artificially stable because the faster it spins, the stronger the centrifugal force is that fights gravity, but that won't last forever. When the food stops coming in, the spin will slow down, and the delicate balance between spinning and fall will break. There will be no explosions or bright flares when the pulsar turns into a black hole at that very moment. It will just stop sending out pulses all of a sudden. From Earth, telescopes will see it as if someone turned on a light switch in space. Instruments aboard NASA on the International Space Station track its pulse timing to microsecond precision, while Fermi and Swift watch for gamma-ray irregularities that might signal structural change. Ground arrays like LOFAR in Europe and the Green Bank Telescope in the US listen for subtle drifts in frequency, searching for evidence of mass gain or internal glitches, tiny starquakes that shake the whole crust. Every fraction of a second matters. If its spin suddenly slows or stops, it could mean the most extreme transformation ever witnessed in real time. What a neutron star really is. It seems a bit of a trick to call a neutron star a star at first. There is no glow, warmth, or light that gives life. The sun's body is all that's left, the weirdest and densest thing the universe can make without breaking the rules of physics. A neutron star is what happens when gravity almost wins. When matter is squished together like this, the words solid and gas no longer make sense. Start with an ordinary massive star, one perhaps 8 to 20 times heavier than our Sun. For millions of years it burns hydrogen into helium, then helium into heavier elements, stacking them like nesting dolls in its core. Iron is the final product, and when fusion reaches that stage, the process can no longer release energy. Fusion stops, but gravity doesn't. The balance breaks. In less than a second, the star's core collapses from the size of Earth to the size of a city, while the outer layers rebound outward in a supernova so bright it can outshine an entire galaxy. What's left at the center is the neutron star, a core so dense it packs more mass than the Sun into a ball just 20 kilometers across. On the surface, gravity is beyond comprehension. If you could stand on it, which you couldn't, a single step would crush you into a smear of subatomic particles. The gravity is about 100 billion times stronger than Earth's, enough that light itself bends noticeably across the horizon. Drop an object from 1 meter above the surface and it would hit at nearly half the speed of light. Yet despite that unimaginable pull, the star doesn't collapse entirely because inside, an equally powerful force pushes back: neutron degeneracy pressure. That pressure is based on quantum mechanics. Neutrons and all fermions don't want to be in the same quantum state, so it exists. They will not give in to being squeezed any further if you get them close enough. This rule is the last line of defense against gravity in a neutron star. The protons and electrons have long since joined together to form neutrons. This has created a kind of cosmic atomic nucleus, a single neutron the size of a city that is held together by gravity and quantum stubbornness. But that pushback can only go so far. The limit set by Tolman, Oppenheimer, and Volkoff shows the limit of that resistance. When you go over about 3 solar masses, even quantum rules give up. A black hole is formed when space falls apart. A neutron star's interior isn't uniform. The crust is only a kilometer thick, but it's harder than any material known to science, 10 billion times stronger than steel. Below that crust lies a sea of superfluid neutrons, flowing without friction, spinning in sync with the star's rapid rotation. This is where some of the weirdest physics in existence plays out. The rotation forms quantum vortices, tiny whirlpools that carry angular momentum through the fluid interior. Occasionally they shift or unpin from the crust, causing the whole star to lurch, an event astronomers call a glitch. When that happens, the pulsar's spin momentarily speeds up, betraying the restless mechanics beneath its perfect rhythm. The magnetic field is just as strong. It comes from the iron core of the parent star falling, and it gets stronger as the star's radius decreases. The magnetic field of a normal neutron star is 1 trillion times stronger than Earth's and can speed up charged particles almost to the speed of light. That's what makes the famous pulsar beams work. The magnetic poles send out narrow cones of radio, X-ray, or gamma radiation. These beams move through space like light from a cosmic lighthouse as the star spins. If one crosses Earth's line of sight, we see a steady pulse. The Black Widow pulsar sits at the far end of this scale. Its spin, over 700 revolutions per second, keeps its structure just barely intact. Any faster and centrifugal force would overcome gravity at the equator, flinging material into space. Any slower, and gravity would crush it further inward. That's why it's unstable. It's living at the edge of what matter can endure. Neutron stars' interiors have been modeled by astronomers for decades, but it is still one of the hardest problems in physics. Normal models can't fit the numbers, and lab tests can't show that they're true. Some scientists believe there is more inside than neutrons. They think it might be quark matter, in which neutrons break down into a soup of their quark parts. Others think that strange states of matter, like hyperons or kaon condensates, are hidden deep inside. Neutron stars aren't just leftovers, if what they say is true. They're actually places where the universe's most extreme tests happen, showing us what happens when matter is pushed past all known limits. Pulsars, cosmic lighthouses explained. Pulsars looked like messages from other people before we knew what they were. Back in 1967, Jocelyn Bell Burnell first noticed perfectly timed blips in her radio data. They were sharp spikes that happened exactly once every 1.3 seconds. She called them LGM1, which stands for Little Green Men. Too many of the signs happened at the same time. There was no way that a natural source could act that way. However, the truth was not what it seemed to be. The waves were not from an alien race, but from something much stronger. A dead star that was spinning as fast as an atomic clock. Astrophysics would be changed forever by those first sightings, which showed a new type of cosmic beacon, the pulsar. A pulsar is a neutron star whose magnetic field and rotation axis are misaligned. That misalignment focuses radiation into narrow beams that sweep through space as the star spins. Each time one of those beams crosses our line of sight, we see a flash, a pulse. To telescopes, that steady rhythm looks like the heartbeat of the universe, ticking across vast distances with impossible consistency. Some pulse once every few seconds. Others, like the Black Widow pulsar, spin hundreds of times per second. From Earth, they appear as steady as a metronome, their timing so exact that astronomers use them as natural clocks to test the laws of relativity. That level of accuracy is astonishing in terms of physics. All of a star's angular momentum, or rotating energy, stays the same when it falls. The radius gets smaller by tens of thousands of times, which makes the spin rate go through the roof. It works the same way as a figure dancer pulling their arms in, but in a much stronger way. Once, a star would spin once every few days. Now it can spin hundreds of times every second. When you add a magnetic field trillions of times stronger than Earth's to that speed, you get a generator that can send radiation beams through whole galaxies. Inside, the neutron star acts like a giant unipolar generator. Charged particles race along magnetic field lines near its poles. Accelerated to relativistic speeds, they emit synchrotron radiation, bursts of radio, X-ray, and gamma light that stream outward in focused cones. Those cones sweep across the sky with every rotation, creating the illusion of a blinking light. But illusion is the key word. The pulses aren't caused by the star dimming or brightening. They're caused by geometry. If the beam doesn't cross Earth, we see nothing. For every pulsar we detect, there are probably 10 others aimed elsewhere, invisible but just as active. This beam geometry also explains why pulsars gradually fade. As they spin down over millions of years, their magnetic fields weaken, the radiation cones widen, and the beams eventually miss Earth altogether. The lighthouse goes dark, not because it stops rotating, but because its light no longer points our way. The Black Widow pulsar is still in its prime though. Its intense magnetic field and incredible spin make its beams razor-sharp and blindingly strong. The radiation sweeps through space with microsecond regularity. A galactic heartbeat that's been pulsing for billions of cycles without missing a beat. Pulsars come in types. There are young pulsars, fresh from supernova explosions, spinning rapidly but losing energy quickly. There are recycled pulsars revived by accreting matter from a companion star. This is where the Black Widow fits. And there are millisecond pulsars, the true speed demons, some rotating over 700 times a second. These are the most precise rotators known, more stable than any atomic clock built by humans. NASA's timing arrays rely on them to test gravitational waves and probe the fabric of space-time itself. The precision is so perfect that tiny variations in the pulse arrival times can reveal incredible details. A delay of a few microseconds might indicate the star has wobbled, suffered a crust quake, or been tugged by a hidden planet. Some pulsars have even been found to host planetary systems, their timing data revealing worlds orbiting a corpse. It's proof that the universe can rebuild from destruction, that death can leave behind order. But not every order is safe. The climate around a pulsar is one of the toughest that is known. Its magnetic poles spit out particles moving at almost the speed of light, making radiation fields that would kill anything close. In a system like the Black Widow, the partner star is not only unlucky, it's doomed. Being hit by those beams over and over again wears away its top layers, leaving only a dying spark. The pulsar gets its name from the way it works, like a hunter eating its prey until nothing is left. Spin up how millisecond pulsars form. It normally spins fast, but not that fast, when a huge star breaks apart into a neutron star. A pulsar that is just starting out might spin a few times every second, slowing down as it sends energy out into space. There are neutron stars that spin hundreds of times per second, which is faster than a jet engine's fans. How does this happen? A slow, violent process called spin-up is what turns an old neutron star into a millisecond pulsar, which is the type of star that NASA watches like a ticking bomb. It is cold and doesn't do anything as it moves through space until it meets another star and forms a binary system. If the two are close enough, gravity starts to pull the outer layers of one into the inner layers of the other. Over many millions of years, gas from the normal star swirls into a transfer stream, enclosing the neutron star in a bright ring. The disk is a swirling mass of plasma moving at almost the speed of light. Each drop that falls in gives the neutron star more mass and speed. It's a cosmic recycling program. The dead star becomes active again, its rotation gradually accelerating as angular momentum from the infalling gas is transferred to its crust. That's how a once slow neutron star transforms into a millisecond pulsar, spinning hundreds of times each second. But the process is as dangerous as it is spectacular. The more material it accretes, the closer it comes to crossing the threshold where neutron matter itself can no longer resist gravity. Every gram added is one step closer to collapse. This fine balance is known as the Eddington limit by astronomers. It is the fastest rate at which a star can take in matter without radiation pressure pushing it away. It is thought that the strong radiation from the falling gas would stop more buildup and keep the flow steady. In real life, that balance is a mess. Matter falls in bursts, magnetic fields push it in different directions, and sometimes powerful X-ray flares appear in some parts of the disk. The Black Widow pulsar is the perfect example of this dangerous dance because it is always eating, always speeding up, and always threatening to break apart. As the neutron star spins up, its magnetic field plays a double role. It both channels the infalling gas and limits how close it can get. The magnetic poles act like funnels, guiding matter into narrow hotspots where it slams onto the surface and releases enormous energy. Each impact heats the crust, and the localized flashes generate powerful radiation beams that sweep across space. The faster the star spins, the more energy those beams carry, turning the system into a cosmic blowtorch. But there is another effect, the barrier of centrifugal force. At the equator, centrifugal force starts to work against gravity as the speed of spin goes up. At some point, the surface speed gets close to a large fraction of the speed of light. For the Black Widow, that fraction is about 20%. That's as far as the star can go before it breaks apart. It is thought that if a neutron star could spin much faster, the outer layers would fly off in sheets of neutron-rich matter, creating a brief ring of debris. That's never going to happen, though. A hard cap is made by friction, magnetic drag, and the science of nuclear matter. The Black Widow pulsar is dangerously close to this cap. The feeding doesn't just make the neutron star spin faster, it changes its structure. As more mass piles on, the core compresses, increasing density and internal pressure. The neutron degeneracy force holding it up weakens against gravity's crush. Simulations show that in these extreme conditions, exotic states of matter may emerge, hyperons, quark matter, or strange particles that exist nowhere else. The entire star becomes a physics experiment, balanced between stability and implosion. At some point, the process turns parasitic. The companion star, stripped of its outer layers, begins to shrink and fade. In the most extreme cases, like the Black Widow system, the neutron star's radiation becomes so intense that it physically ablates its partner, burning it away atom by atom. The name isn't metaphorical, it's the stellar version of the spider devouring its mate. The companion dwindles into a faint white dwarf, or vanishes entirely, leaving behind a neutron star bloated with stolen mass and spinning at near relativistic speeds. This process also explains why millisecond pulsars are older than they look. Many of them are billions of years old, ancient corpses revived by fresh fuel. Their surfaces may be cool, but their spin tells a story of violence and survival. They've lived two lives, one as the core of a massive star, the other as the predator in a binary system. That second life is what makes them dangerous, because the price of revival is instability. Astronomers have sometimes seen systems freeze in the middle of spinning up. There are small changes in the pulsar's time trends that suggest it's getting close to the end of its feeding cycle. What happens when the partner star is gone? The neutron star stops gaining mass, its spin slows down, and the system goes quiet. But if it goes over the imaginary line first, adding just a little too much mass, it falls apart right away. There was no blast, no notice, and no second chance. The 707 Hertz record. Scale is often used to measure speed in science. Planets go around stars and galaxies spin, but experts are always amazed by one number, 707 Hertz. This is how fast the Black Widow pulsar spins. 707 full turns every second. So far out there that not even NASA's most advanced atomic clocks can keep up with its beat. Every heartbeat that hits Earth comes at the exact same time, faster than the blink of an eye and more steadily than any machine people have ever made. To grasp how fast that really is, imagine standing at the equator of this star, if such a thing were possible. The surface would be moving at more than 150,000 kilometers per second, nearly half the speed of light. That's fast enough to circle Earth 4 times in the time it takes you to read this sentence. And yet, gravity holds it together. The same force that would crush a mountain into dust also keeps a structure spinning at relativistic velocity from flying apart. It's an impossible balance that should not exist, but it does. Astronomers spent decades searching for the fastest possible pulsar, scanning the skies with radio telescopes, timing thousands of candidates, and filtering out false signals caused by interference. The first millisecond pulsar, discovered in 1982, spun at 642 times per second. An astonishing number back then, but scientists suspected there were faster ones out there, hidden by weak signals or narrow beams that missed Earth. It wasn't until observations from LOFAR and later Green Bank telescope confirmed it. A 707 Hz rotation, belonging to a small, dim source roughly 14,000 light-years away. It shattered the previous record and set a new benchmark for what nature could achieve. Here's why that number matters. A neutron star's maximum spin rate isn't random, it's defined by physics. If it spins too slowly, its magnetic field decays and its pulse weakens. But if it spins too fast, centrifugal force at the equator starts to counteract gravity. At a certain threshold, somewhere between 1,000 and 1,200 rotations per second, the crust would tear apart. The Black Widow pulsar is perched just below that limit, meaning we are seeing it in its final stable configuration, its nature running as close to the red line as it dares. At 707 Hz, the shape of the pulsar changes in a strange way. It's no longer round. Now it's oblate, with flattened sides and a bulging center like a spinning water droplet. The top is under a lot of stress and is always close to breaking. Under it, superfluid neutrons spin in perfect sync with each other and store rotational momentum in quantum vortices. In each spiral, there is a thin thread of spinning space-time, that goes through the whole star. These swirls move every once in a while, releasing energy in microquakes that change the timing of the pulsar by milliseconds. These are the glitches that keep scientists guessing. At such speeds, even time behaves differently. According to relativity, clocks on the surface of the pulsar tick slower than those far away, distorted by its immense gravity and motion. A second near the crust passes slightly slower than a second on Earth, but that lag is built into every pulse we detect. It's a living demonstration of Einstein's theories, one that repeats 700 times per second, like a cosmic experiment running endlessly in the background. That consistency is what makes pulsars like this invaluable to NASA. The NICER instrument on the International Space Station measures their timing to within microseconds, using them as navigation beacons. In principle, a spacecraft anywhere in the galaxy could triangulate its position just by comparing the arrival times of several pulsar signals. The Black Widow pulsar, with its ultra-stable frequency, could one day serve as part of a galactic GPS, a system built on the corpses of dead stars. The high speed, on the other hand, makes it unstable. When a star spins that fast, it puts a lot of centrifugal stress on its inside, which makes the gravity pull that is already pushing it toward collapse even stronger. It adds mass and rotational momentum with each extra atom it steals from its partner, making the balance even tighter. There is a chance that it will explode if its mass increases by even a small amount, like a few hundredths of a solar mass. That's why this record isn't a tribute to toughness. This is a warning sign. Weighing a star near the limit. The whole story changed when scientists found out that the Black Widow pulsar wasn't just fast, it was also heavy. While speed alone can be impressive, mass is what determines fate. This star has almost 2.5 times the mass of the Sun in a body no bigger than a small city. Not only is that heavy, it's near the edge of being real. There is a line in the world that not even matter can cross. You can't go back after going past it. You stop being a star and turn into a black hole. Measuring that kind of mass is no easy task. You can't just weigh a neutron star on a cosmic scale. Instead, astronomers use its orbit as a balance beam. The Black Widow system is a tight binary, meaning the pulsar and its companion star dance around a common center of gravity. By watching the tiny shifts in timing between pulses, microsecond differences caused by orbital motion, scientists can calculate the mass of both objects. It's called pulsar timing analysis, and it's so precise it can measure motion smaller than the width of a human hair across thousands of light years. What they found shocked everyone. It was found that the pulsar had a mass of about 2.35 solar masses, which makes it the largest neutron star ever proven. That record may seem random, but in the field of physics, it's huge. A possible upper limit is called the Tolman-Oppenheimer-Volkoff limit, or TOV limit for short. It shows how much mass a neutron star can hold before gravity becomes too strong and the star falls apart into a black hole. Models put the ceiling somewhere between 2.5 and 3 solar masses, but they aren't sure. This star is almost certain to go out of existence because it is perched on the edge of a cliff. Make a ball 20 kilometers wide and put every rock, ocean, and planet in the solar system inside it. Think about that ball being 2.4 times heavier than the Sun. We're talking about solids that are over 1 billion tons per cubic centimeter dense. Matter doesn't act like atoms inside that impossible sphere. Nuclei have broken apart. Protons and electrons have joined together, and neutrons are squished together like marbles under endless pressure. Deeper inside, those neutrons might even split into quarks, making what scientists call quark-gluon plasma, a strange material that was there microseconds after the Big Bang. For physicists, the Black Widow's mass isn't just impressive, it's a puzzle piece in one of astronomy's biggest questions. What is matter's breaking point? The higher the confirmed mass of a neutron star, the tighter we can constrain nuclear physics models. If neutron matter can support more than 2.5 solar masses, it means our understanding of strong nuclear forces needs an upgrade. If it can't, then this pulsar's days are numbered. Either way, its existence stretches theory to the limit. What's left of it is a faint ember-like white dwarf that is about 0.02 solar masses lightweight, or about as heavy as Jupiter. There is only a ghost of a star that used to be full because the pulsar is pulling on it so hard. It goes around the sun every few hours, so radiation is always hitting its surface. One side gets very hot, thousands of degrees, while the other side stays cold. The end result is a horrifying half-burned sphere that glows unevenly like a lamp whose light is going out. Scientists can figure out how strong the pulsar's gravity must be to cause that shift by modeling how the light from the companion changes during rotation. This gives them another clue about the mass of the system. It always comes down to the same thing. This thing is too big to be comfortable. The Tolman-Oppenheimer-Volkoff ceiling. Things in the universe all have limits, or points where they can't hold up their own weight any longer. That point is reached for buildings when steel and concrete give way. It's when the planet's gravity turns rock into metal. For neutron stars, that line is written in basic physics as the Tolman-Oppenheimer-Volkoff limit. This is the point at which even the quantum rules of matter give way to gravity. The Black Widow pulsar, which is the largest neutron star known to science, lives just outside of that line. It's like a building in space that moves with the wind. The TOV limit takes its name from three scientists, Richard Tolman, J. Robert Oppenheimer, and George Volkoff, who in 1939 asked a question few dared to. How massive can a neutron star be before collapsing into a black hole? They combined Einstein's general relativity with nuclear physics to find an answer. The result wasn't a precise number, but a threshold, somewhere between 2 and 3 times the mass of the Sun, depending on how matter behaves under extreme pressure. It's not a sharp cliff, but a fog-shrouded boundary, the point where neutron degeneracy pressure can no longer counteract gravity. To understand what happens near that limit, imagine a neutron star as a balancing act between inward pull and outward push. Gravity wants to crush everything into an infinitesimal point. The neutrons inside resist, not through strength, but through quantum rules. Neutrons can't occupy the same quantum state, so when you pack them tightly, they generate a counterpressure that holds the star up. But this defense has limits. As mass increases, gravity's pull rises faster than neutron pressure can respond. Eventually, even quantum mechanics runs out of tricks. The result? Implosion. The Black Widow pulsar's 2.35 solar masses place it squarely in the danger zone. If its mass creeps up even slightly, by a few percent, the inward pull could overwhelm its structure. Inside, the core would collapse first, followed by the outer layers falling inward at nearly the speed of light. No shockwave, no explosion, just a silent implosion that traps light itself. What remains would be a black hole, only a few kilometers wide, invisible except for the gravitational fingerprint it leaves behind. That transformation would happen faster than human comprehension. The surface would cave inward in milliseconds, the magnetic field would snap, and the pulsar's famous radio beams would cut off mid-pulse. From our perspective, one instant, we'd detect its rhythmic heartbeat. The next, nothing. The universe would have erased a signal it had been broadcasting for eons. But to understand why this collapse hasn't happened yet, scientists look to rotation. The Black Widow's rapid spin adds a stabilizing force, centrifugal support that acts against gravity. Every revolution, 707 per second, creates a faint outward push at the equator, easing some of the internal pressure. It's a temporary reprieve, buying the star more time before the inevitable, yet this balance is precarious. As radiation drains its energy and the star's spin slows over millions of years, that stabilizing effect will weaken. The TOV limit will close in. No one knows exactly what matter looks like at those densities. Traditional models assume it's made mostly of neutrons, but some theories propose exotic matter, particles like hyperons or deconfined quarks that appear only under extreme pressure. If such particles form, they soften the internal pressure, effectively lowering the TOV limit. That means the true threshold might be even smaller than we think. If that's the case, the Black Widow pulsar could already be living beyond the point where theory says it should exist. A cosmic paradox, surviving through rotation alone. This is why finding the masses of neutron stars isn't just a matter of recording things, it's also a matter of trying the rules of physics. With each new high-mass discovery, scientists have to make their models of how nuclei communicate with each other better. As soon as the Black Widow's mass was proven, scientists had to re-evaluate calculations that had been accepted for decades. Some people even came up with new types of matter called strange quark stars as a possible answer. Neutrons have broken down into free quarks in those models, creating a uniform, very thick liquid that can withstand gravity for longer. This is a whole new type of object if the Black Widow is one of these. It's not just the biggest neutron star. Accretion torque, when feeding adds spin. All stars eat, but some eat so fast that they change the rules of physics in the process. Another type of cosmic eater is the Black Widow pulsar. It is a neutron star that got its speed, heat, and mass by eating its smaller, weaker partner. It's not a nice act. This process, called accretion, gives the pulsar its huge amount of energy and is also the reason it will finally fall apart. Every meal gives you strength and stress. It gets closer to the point where it can't go back with each gram it eats. Accretion starts with gravity's simplest trick: imbalance. The pulsar's gravitational field is so strong that its companion star, a faint remnant about the size of a planet, can't hold on to its own outer layers. The gravitational pull between them creates a bridge of plasma, a river of matter flowing from the companion toward the pulsar. That stream forms a glowing whirlpool called an accretion disk, spiraling inward at a fraction of light speed. Friction within that disk generates staggering heat, producing X-rays that outshine thousands of ordinary stars. But the real magic happens at the boundary, where the disk meets the pulsar's magnetic field. The field acts like a cosmic gearbox, converting the falling matter's motion into rotational energy. As particles spiral along the magnetic field lines and slam into the pulsar's surface, they transfer angular momentum. The result is accretion torque, the process that spins the neutron star faster and faster with every gram it consumes. This mechanism is what resurrects old neutron stars into millisecond pulsars. Over millions of years, the accreted material acts like a cosmic hand on a flywheel, gradually accelerating it until it becomes one of the fastest rotating objects in existence. The energy released is mind-boggling. Even a small amount of infalling gas, about the mass of a car, can release more energy than the sun emits in an entire day. But that spin-up comes with a cost. The pulsar's magnetic field, once strong enough to halt accretion entirely, begins to weaken as it's buried beneath fresh layers of matter. That weakening allows even more material to fall inward, feeding the cycle further. The more it eats, the faster it spins. The faster it spins, the more it destabilizes its magnetic defenses. It's a self-reinforcing feedback loop, a slow-motion disaster disguised as growth. In the Black Widow system, this process is particularly brutal. The companion star, reduced to a fraction of its original size, is caught in a death spiral. The pulsar's radiation bombards it constantly, heating one hemisphere to thousands of degrees, while the other remains cool and dark. The temperature difference drives powerful stellar winds, which strip even more gas from the companion surface. That material doesn't just escape, it's funneled straight into the pulsar's grasp. Bit by bit, orbit by orbit, the companion is devoured. Another thing that this slow feeding does is keep the pulsar spinning at a pretty steady speed. The pull from electromagnetic radiation is balanced by the torque from accretion, which sets up a brief balance. But the key word is temporary. The spin will start to break down once the partner is gone and there is no more stuff to steal. The pulsar will lose the outer push that keeps it stable against gravity. This is the only thing that is keeping it from falling in on itself. Astronomers have measured the Black Widow's torque directly by studying subtle variations in its pulse timing Each tiny shift in frequency tells them how the star's mass and angular momentum are changing. These changes happen so gradually that it takes years of continuous observation to notice, but when compiled, they tell a clear story. The pulsar is still gaining. Its spin has stabilized, but its mass continues to climb ever closer to the theoretical limit. That's why NASA and other observatories monitor it almost constantly. One small uptick in mass could spell the end. If accretion continues, the system could reach a tipping point. As the pulsar's gravitational field strengthens, it can begin pulling in material faster than radiation can repel it. When that happens, the accretion rate skyrockets, flooding the surface with energy and creating a brief, blinding flare of X-rays. It's the final meal before collapse, a flash announcing that the neutron star has eaten itself past stability. After that, everything would go quiet. The pulses would stop, the X-rays would vanish, and the only sign left would be the gravitational fingerprint of a newborn black hole. Black widow pulsars eating the companion. If there's one type of star that lives up to its name, it's the black widow pulsar, which eats its partner until nothing is left. The black widow relationship is harsh and one-sided, unlike most binary systems where the two sides live in a kind of delicate gravity balance. One star is hurt. It's a small, weak mass that's bleeding into space. The pulsar, on the other hand, is the killer, taking away its partner atom by atom as it spins towards death. The name Black Widow isn't poetic exaggeration. It's literal astrophysics. Just as the spider consumes its mate after reproduction, these pulsars destroy the very star that helped revive them. The process begins innocently enough. The neutron star, long dormant after its supernova birth, draws close to a lower mass companion. Over time, gravity creates a bridge between them, a Roche lobe, where matter from the smaller star spills over into the neutron star's gravity well. Once the first atoms start to flow, the process accelerates. The neutron star devours the fresh fuel, and the more it eats, the stronger its pull becomes. But the real violence comes not from gravity, but from radiation. Every rotation of the pulsar generates beams of high-energy particles and gamma rays that slam into its companion's surface. The bombardment is relentless. It vaporizes the outer layers of the smaller star, heating one hemisphere to thousands of degrees while leaving the other side dark and cold. That heat drives a supersonic wind, a steady outflow of gas that the pulsar's gravity captures and channels into its accretion disk. It's a system powered by both hunger and cruelty. Radiation strips the star, and gravity eats what's left. We are amazed that we can watch this process happen live. The partner is no longer round, it's stretched out like a teardrop, and its light flickers as it moves around. Every few hours, telescopes see the light getting brighter and darker in time with the pulsar's spin. The bright side faces the pulsar and is burning orange from being so hot, but the dark side can't be seen. From Earth, it looks like a burning spark going around a terrible light. Over millions of years, the pulsar's victim dwindles. A typical Black Widow companion starts off roughly half the Sun's mass, but is eventually whittled down to less than 0.05 solar masses, lighter than Jupiter. Some shrink to planetary size before evaporating completely. In extreme cases, the companion star is fully destroyed, leaving behind an isolated millisecond pulsar spinning at incredible speed. That's the endgame. The widow star survives, alone, having devoured its mate. The Black Widow system we're focused on is the most extreme of them all. Its companion is already a ghost, barely visible, glowing faintly under the glare of the pulsar's radiation. The two orbit each other in just over 6 hours, separated by less distance than the radius of our Sun. The pulsar's gravity distorts the companion so badly that it's nearly being pulled apart. Each orbit, more material is torn free and funneled into the neutron star's magnetic grip. Some of it lands directly on the surface, adding mass and spin. The rest escapes as high-speed plasma winds, forming a faint tail stretching thousands of kilometers into space. The violence of this relationship extends beyond light and heat. The constant radiation bombardment produces powerful shock fronts between the pulsar wind and the companion's escaping atmosphere. Where those fronts meet, charged particles collide, producing bursts of X-rays and radio waves detectable from Earth. In a way, the Black Widow's orbit is a miniature particle accelerator, nature's version of CERN, running non-stop for millions of years. But there is a limitation. The pulsar is getting closer to collapsing as it uses more mass. It's making its own grave by eating its buddy. Each atom that is eaten raises the pressure inside the particle, moving it closer to the Tolman-Oppenheimer-Volkoff limit. In this sad circle, the death of one star ensures the death of another. The pulsar's core will eventually give way if the partner doesn't go away first. Neutron pressure will not be enough to stop gravity, and the system will end in quiet. The waves that used to beat like a galaxy's heart will stop, and in their place will be the empty shade of a new black hole. Not all Black Widows are identical. Some evolve into redback pulsars, where the companion is heavier and still partially intact. Others transition back and forth between states, toggling between bright X-ray outbursts when accretion dominates and radio pulses when it doesn't. These systems show that pulsars aren't static. They're dynamic ecosystems where gravity, radiation, and magnetism constantly trade dominance. But in the end, the outcome is always the same. One star dies and one survives, for a while. White dwarf donors stripped to embers. Every animal that eats something leaves behind bones. In the story of the Black Widow pulsar, those bones are glowing, faint, white-hot pieces that are moving around in the dark. This system's small broken friend isn't just any dead star. Astronomers call it a white dwarf, which means a star that has already died once and is now going through a second death by fragmentation. These white dwarf donors are the leftovers of stars that used to be like suns, but have been burned out, squished, and stripped layer by layer until there is just a faint spark left. To understand what's happening to this white dwarf, you need to rewind its life. Billions of years ago, it was a normal star, burning hydrogen, fusing helium, and shining steadily. Eventually, it exhausted its fuel and collapsed inward, its outer layers blown off into a planetary nebula. What was left behind was the core, a sphere of carbon and oxygen only about the size of Earth, but half the mass of the Sun. White dwarfs are stable under the pressure of electron degeneracy, another quantum mechanical rule that prevents electrons from being squeezed too close together. They don't shine from fusion anymore. They glow from leftover heat, slowly cooling over billions of years. But in a binary with a neutron star, that peaceful ending doesn't last. The white dwarf becomes trapped in its companion's gravity well, and balance turns to submission. The pulsar's intense radiation begins to cook its surface, vaporizing material into a stream of gas that spirals toward the neutron star. The once quiet ember becomes a fuel source, feeding a cosmic engine far more powerful than anything it could have imagined. Over time, that feeding hollows it out. The white dwarf's mass drops from roughly 0.5 solar masses to less than 0.02, barely heavier than Jupiter. Its structure distorts from a perfect sphere into a teardrop shape, with the pointed end always aimed toward the pulsar that's consuming it. Astronomers have measured these white dwarf remnants in exquisite detail using optical and X-ray data. What they see is shocking. Dayside temperatures reaching 10,000 Kelvin, hotter than many main sequence stars, while the night side stays hundreds of times cooler. The result is a world in perpetual imbalance, its surface boiling on one side and freezing on the other. Each orbit, that extreme temperature difference drives new streams of material toward the pulsar, maintaining a slow, steady death spiral. The radiation from the pulsar doesn't just strip mass, it changes chemistry. The bombardment breaks molecules apart, ionizes atoms, and may even transmute lighter elements into heavier ones through fusion driven by tidal heating. The outer layers of the white dwarf are being peeled off like an onion, exposing deeper, denser material with every cycle. Eventually, Even the carbon-oxygen core may begin to erode. What remains will be a fragment of degenerate matter so small it blurs the line between star and planet, something no longer massive enough to shine, yet too dense to decay. What's scary is how strong these donors can be. Even though they are abused all the time, some last for billions of years, with orbits that get smaller over time but never quite fall apart. Astronomers can study both sides of the binary evolution process, how stars die and how their deaths bring another star to life. Scientists can figure out how much energy the pulsar puts out and how strong its magnetic field is by watching how its beams heat and evaporate the white dwarf. The neutron star's heartbeat can be seen in every flash in the white dwarf's light. The white dwarf's slow demise also helps researchers understand where planets and stellar remnants may end up after supernovae. In some scenarios, these stripped-down donors might survive long enough to escape entirely, ejected from their orbit once the pulsar collapses or loses mass. If that happens, they could drift through the galaxy as rogue remnants, Earth-sized spheres of degenerate matter, dark and silent, the leftovers of cosmic cannibalism. Silent collapse, how a pulsar vanishes. A final bright supernova that can be heard across space for hundreds of years is how most stars say they are dying. Though when a pulsar like the Black Widow hits the end of its stable range, there is no explosion, shockwave, or other sign. It is quiet, happens instantly, and can't be stopped when a neutron star falls into a black hole. At one point, it looks like a lighthouse in space, spinning and flashing in perfect time. The beats stop for good the next second. There is no light or sound, just nothing. This is how a heartbeat is erased by the world. To understand that moment, picture the balance inside a neutron star. Its entire existence depends on a delicate standoff between two forces, gravity pulling inward and neutron degeneracy pressure pushing outward. That outward force comes from quantum mechanics, specifically the rule that no two neutrons can occupy the same space with the same energy. It's the same principle that keeps white dwarfs from collapsing, but here it's working under conditions so extreme that a teaspoon of material weighs billions of tons. For a while, this balance holds. But as the pulsar feeds on its companion, adding more mass, the equilibrium begins to fail. The danger zone comes when the pulsar's mass nears what's called the Tolman-Oppenheimer-Volkoff limit, roughly between 2.5 and 3 solar masses. Cross that line, and no known form of pressure can stop gravity from taking over. When that happens, the star doesn't explode, it implodes. The core collapses inward faster than light can escape. Every atom, every particle, every trace of structure is crushed into an infinitely dense point. The event horizon forms almost instantly, sealing the system off from the rest of the universe. For astronomers, the tragedy of this process is that it would happen invisibly. A pulsar collapse wouldn't release a bright burst like a supernova. It would simply vanish from all wavelengths. The steady rhythm of radio pulses that once arrived every millisecond would suddenly stop. Instruments that had been timing it for decades would register nothing but cosmic background noise. Somewhere in that silence, a black hole would now exist. Unseen, but unmistakably real. That doesn't mean there is no sign of the change, though. The crash would temporarily change the shape of space-time, sending out a burst of gravity waves that would spread out at the speed of light. As the star fell apart, these waves would carry information about its end shape, spin, and how its mass was distributed. The dying signal is a short, sharp sound that marks the moment a neutron star turns into a black hole. If scanners like LIGO or Virgo were sensitive enough, they could pick it up. In terms of astrophysics, it would be like hearing a single note before everything goes quiet forever. There's also the matter of the accretion disk, the ring of gas still swirling around the pulsar at the time of collapse. When the neutron star gives in, the gravitational well deepens abruptly, pulling the inner disk inward. Some of that material crosses the new event horizon, while the rest slams into itself, heating to billions of degrees. For a few seconds, the system might shine brighter than ever, releasing a surge of X-rays and gamma rays before fading again. Then, as the last of the disk vanishes, the light dies too. What remains after this transformation is a black hole barely distinguishable from any other. Its mass and spin are preserved, but its magnetic field, once the driving force behind the pulsar's beams, disappears. The radio emissions stop, the X-rays fade, and the system becomes quiet. Yet its gravitational influence persists, shaping the orbit of any remaining debris or companion star. If the white dwarf hadn't been completely consumed, it would now orbit an invisible partner, unaware that the cosmic lighthouse it once circled is gone forever. This kind of collapse isn't just theoretical. Astronomers have identified several missing pulsars, neutron stars whose emissions stopped unexpectedly, suggesting that they might have crossed the threshold and vanished into black holes. These events are rare but invaluable. Each one offers a real-time look at the thin boundary between matter and nothingness. If we ever detect a collapse as it happens, it could confirm long-standing predictions about how matter behaves under the strongest gravity nature allows. This is why the Black Widow pulsar is almost always being watched by NASA and other telescopes. Timing data gathered over many years can show small changes in pulse frequency or spin, which are hints that the star is still adding mass or its structure is changing. Even a small slowing down in spinning or a tiny loss of brightness in the X-ray could mean that forces inside the object are giving way. Once the pulses stop, the data will become flat. That's when a new black hole, 14,000 light-years away, was born. Magnetars versus pulsars, different threats. While all neutron stars are extreme, magnetars take the word and twist it in a way that makes it almost impossible to understand. While pulsars are precise time tools that are steady, regular, and clock-like, magnetron instruments are chaos itself. They can be dangerous even if they're not spinning at a very high speed. They don't even have to move. Their magnetic fields are strong enough to break apart atoms, bend the surfaces of planets, and send bursts of high-energy radiation into space, lighting up the galaxy. Magnetars are like cosmic landmines. They don't make a sound until they go off. Pulsars are like cosmic lights. The line between a pulsar and a magnetar starts with the same origin story. Both are born from the collapse of massive stars, compacted into spheres barely 20 kilometers wide, but containing more mass than the Sun. The difference lies in what happens inside their cores. While ordinary neutron stars freeze their magnetic fields at a manageable strength, around 1 trillion times Earth's, magnetars twist those same fields to 1,000 trillion. That's a quadrillion times stronger than what compasses or MRI machines could ever handle. It's the strongest magnetic field known anywhere in the universe, and it's unstable by nature. The physics of such a field is hard to grasp. Near the surface, the magnetic stress is so intense it literally reshapes matter. Electrons are forced into linear paths along magnetic field lines, compressing atoms into cigar-shaped forms. The crust, an iron-rich shell only about 1 kilometer thick, buckles under the tension. It creaks, shifts, and occasionally cracks, releasing energy equivalent to billions of nuclear bombs. These events are called starquakes, and they are the reason magnetars flash. When the crust snaps, the magnetic field lines reconnect and release gamma rays and X-rays powerful enough to be detected across the galaxy. On December 27, 2004, one of these events became famous. A magnetar called SGR 1806-20, which is 42,000 light-years away in the constellation Sagittarius, sent out a burst that was so strong that it quickly threw off satellite monitors. For a very short time, it was the brightest source of X-rays in the whole sky. The flare was so strong that it hit the Moon and then hit Earth's atmosphere again, making it a little more charged. The ozone layer around Earth would have been cleared away if it had happened within 10 light-years. Even though it was 42,000 light-years away, it still had an effect on us. The terrifying part? Magnetars aren't rare in theory, just short-lived. Their extreme magnetic fields decay quickly, fading within 10,000 to 100,000 years. That's the blink of an eye on cosmic timescales. During that brief lifespan, they exist in a constant state of pressure buildup and release. Astronomers think there are about 30 known magnetars in our galaxy, and perhaps hundreds more hidden behind dust or disguised as ordinary pulsars. Because they fade so fast, catching one in action is like spotting a lightning bolt halfway through the strike. Pulsars, by comparison, are tame. Their magnetic fields, though intense, are stable. They rotate at astonishing speeds, but they rarely explode. They lose energy slowly over millions of years, dimming gracefully as their spin slows. Magnetars, on the other hand, burn out violently. Their energy isn't rotational but magnetic, and it decays in sudden outbursts. That difference in energy source makes magnetars unpredictable. Quiet one day, apocalyptic the next. The contrast between these two kinds of neutron stars helps scientists understand just how broad the spectrum of stellar remnants can be. Pulsars are born from normal supernovae, often spinning rapidly because of the conservation of angular momentum during collapse. Magnetars might result from even more massive stars, ones whose cores spun slower but trapped more magnetic energy. That energy is wound up during the explosion and frozen into the newborn neutron star, setting up the internal stresses that define its violent life. The two also behave differently. Pulsars emit beams of radio waves or X-rays that sweep across Earth like a clock, creating the rhythmic pulses we can measure precisely. Magnetars, meanwhile, shine erratically in X-rays and gamma rays, flaring at random. Their emissions can brighten by a factor of 1,000 in seconds, then fade back to near invisibility. When these flares occur, they can briefly rival the brightness of an entire galaxy. That's why space agencies keep a constant watch. Magnetars are the ultimate cosmic wildcards. The setting they make is another important difference. A magnetar's magnetic storms can speed up particles to incredible energies, creating bursts that move through space as fast radio bursts, which are short flashes of radio energy that happen once and don't happen again very often. Magnetars have been linked to some of these FRBs, which suggests that the same type of starquakes that cause gamma-ray flares can also send out radio waves strong enough to cross galaxies. Starquakes and giant flares in action. Picture a world that is made of nothing but metal. It would have a thick crust of iron that covers a sphere 20 kilometers wide, spins faster than any planet, and holds in forces that are hard to imagine. Picture that crust breaking, not slowly or without notice, but all at once and very violently. Astronomers call this a starquake, and it's one of the worst natural events that can happen in the world. For magnetars and unstable pulsars alike, starquakes are like tectonic changes in the universe. But instead of moving countries, they send out energy that can light up galaxies. A starquake begins deep within a neutron star's crust. The surface, though rigid, is constantly under strain from the magnetic field that runs through it. The field lines twist and tighten over time, locked into place by the star's superdense matter. But magnetic fields don't like being tangled. They build stress as they try to realign. When that stress surpasses the strength of the crust, it snaps. In less than a millisecond, enormous sections of the surface shift, releasing an explosion of gamma rays and X-rays so intense it can saturate space telescopes thousands of light years away. The most famous example came from the magnetar SGR 1806-20 in December 2004. For just 0.2 of a second, it outshone the rest of the Milky Way combined. The energy released in that blink was equivalent to what our Sun emits in 250,000 years. Detectors on multiple satellites went blind. Even 42,000 light-years away, the burst caused measurable changes to Earth's upper atmosphere. That's the scale of a starquake, an event so massive it shakes planets that never even knew it happened. Scientists have identified 3 main stages in such a flare. First comes the precursor burst, a small spike of X-rays marking the moment when cracks begin forming in the crust. Then the main flare, when the magnetic field violently reconfigures, ejecting matter and radiation in all directions. Finally, the afterglow, a tail of soft X-rays that lingers for hours or days as the magneta's surface cools back down. These stages unfold faster than any earthquake, yet their power dwarfs every natural disaster in cosmic history. One theory proposes that magnetic reconnection, the same process that drives solar flares, scales up dramatically in a magnetar's environment. When the field lines break and reconnect, they accelerate charged particles to near light speed, generating high-energy radiation in the process. The crust itself acts like a resonating shell, vibrating under the strain, sending seismic waves rippling through the star's body. Those vibrations, in turn, modulate the emitted light, allowing telescopes to measure the ringing of the neutron star like a bell struck by gravity. For magnetars, starquakes are both a release and a warning. Each one relieves some magnetic stress, but also fractures the crust further, making future quakes more likely. Over time, the surface becomes a patchwork of fault lines, and the magnetic field loses coherence. This decay is why magnetars live fast and die young. Within tens of thousands of years, their power fades as their fields unwind and their energy dissipates. But during that short lifetime, their flares can reshape the interstellar environment around them, ionizing gas clouds and heating dust across entire star-forming regions. Pulsars like the Black Widow don't normally experience flares on that scale, but they aren't immune to smaller versions of the same phenomenon. In these cases, it's rotational energy rather than magnetic stress that drives instability. As the pulsar's crust adjusts to changes in spin, sudden shifts called glitches can occur. A glitch is a micro-starquake. The surface briefly moves, releasing tension and causing the pulsar's rotation rate to jump by a fraction of a percent. These events are short but detectable. They tell scientists that even a neutron star, seemingly solid and unbreakable, flexes under its own physics. The time of these tremors is what makes them so intriguing. Some magnetars don't do anything for years before they explode. Others show up more than once in a month. Astronomers are always on guard and keep an eye on known candidates around the clock because they can't tell what will happen. The NICER, SWIFT, and Fermi gamma-ray space telescopes all keep an eye out for the next spike and are ready to record it. When they catch one, it gives them a chance to study extreme matter in conditions that could never be made in a lab. The 2004 Sagittarius Blast. It came out of nowhere, a flash so quick that most people didn't even notice, but it was so strong that it changed the whole sky for a moment. On December 27, 2004, the brightest cosmic event ever seen from within our own galaxy was caught at the same time by telescopes on Earth and satellites in space. As far as we can tell, it wasn't from a supernova or a gamma-ray burst. It came from a magnetar that was quietly sitting in Sagittarius, which is 42,000 light-years away from Earth. It's called SGR 1806-20. This thing put out more energy in 0.2 of a second than the Sun does in 200,000 years. The event was so intense that it saturated every detector aimed at the sky. NASA's SWIFT, Integral, and RESI satellites all went temporarily blind as the flash overwhelmed their sensors. Even the Voyager 1 spacecraft, far beyond the orbit of Pluto, recorded a sudden spike in gamma radiation, proof that the wave of energy reached the outer edges of the solar system. For a brief instant, this one neutron star outshone every other X-ray source in the Milky Way combined. The burst's energy release was almost beyond imagination. In just 0.2 of a second, the magnetar unleashed about 10 to the power of 46 joules, roughly equal to the detonation of 100 trillion nuclear bombs at once. The radiation wave reached Earth's upper atmosphere, ionizing a thin layer of gas and briefly distorting global radio signals. No other natural event beyond our solar system has ever been powerful enough to physically alter Earth's atmosphere, but this one did. What makes this story even stranger is how quiet things seemed just before it happened. SGR 1806-20 had been classified as a soft gamma repeater. a type of magnetar that occasionally emits bursts of gamma rays when its magnetic field rearranges. But in late 2004, it showed no major signs of instability. Its rotation period, about 7.5 seconds, was steady. Its X-ray flux was stable. Then, on that December day, the crust cracked. The magnetic field lines twisted and snapped back, ejecting an explosive burst of energy into the vacuum of space. The timeline of the event was recorded in fine detail. The first pulse, lasting just 0.2 seconds, carried 99% of the total energy. That was followed by a fainter, oscillating afterglow that persisted for minutes. The initial flash was so bright that it caused a phenomenon called photon pileup, where detectors simply couldn't process photons fast enough to distinguish them individually. It was like trying to count raindrops during a hurricane. Astronomers later realized they were lucky. If SGR 1806-20 had been located just 10 light-years away, the consequences for Earth would have been catastrophic. The gamma radiation would have destroyed the ozone layer, allowing ultraviolet light from the sun to sterilize the planet's surface. As it was, even from 40,000 light-years away, it served as a cosmic warning shot. The universe had just reminded us that it can unleash devastating energy without so much as a whisper of preparation. In the aftermath, scientists scrambled to model what had happened. The best explanation remains a magnetic reconnection event, essentially a titanic version of a solar flare. The magnet's field lines had been twisting within its crust for centuries. When the crust finally cracked, those lines snapped and reconnected in a fraction of a second, converting magnetic energy into heat, radiation, and kinetic force. The star's surface likely vaporized and then resettled, glowing faintly for days as it cooled. Follow-up observations revealed that the magnetar's spin had slowed slightly after the flare, suggesting that angular momentum was carried away by the explosion. Its magnetic field, though still intense, had rearranged, releasing stored tension. That's consistent with the idea that magnetars don't explode just once. They rupture, heal, and repeat, each cycle chipping away at their stability. Over thousands of years, that process eventually drains their magnetic energy, turning them into quieter, less active neutron stars. The 2004 Sagittarius event wasn't just a record-breaking flare. It was a watershed moment for astrophysics. It provided the first direct evidence that magnetars could produce bursts powerful enough to mimic gamma-ray bursts, GRBs, which were previously thought to occur only in distant galaxies from collapsing stars. For years, astronomers had been puzzled by short-duration GRBs, flashes lasting less than 2 seconds that seemed to appear randomly across the sky. After the Sagittarius flare, it became clear that some of those short GRBs might not be distant explosions at all, but local magnetar flares seen from other galaxies. Birth of jets after a collapse. It's quiet when a neutron star finally turns into a black hole, but the noise it makes afterward can be heard all over space. After the system collapses, it turns into one of the most powerful particle engines in the universe for a short time. It sends out relativistic jets that burn through the darkness like cosmic flames. A star that is falling sends out these jets, which are narrow beams of plasma moving very fast, taking away the last bits of its magnetic field and angular momentum before gravity shuts the door for good. The birth of these jets begins in chaos. Inside the neutron star, as it nears the collapse threshold, the balance between gravity and nuclear pressure disintegrates. The core implodes inward, crushing matter faster than light can escape. At that same instant, the magnetic field lines that once anchored the pulsar's beams are dragged down and twisted into knots. The infalling plasma, unable to fall straight in because of the star's spin, forms a temporary accretion disk around the newborn black hole. That disk becomes the launch pad. In the milliseconds after formation, the black hole and its disk act like an electromagnetic dynamo. The disk's inner edge rotates at a fraction of light speed, generating enormous magnetic stress. Through a process known as the Blandford-Znajek mechanism, energy from the black hole's spin and magnetic field is converted into kinetic energy, flinging particles outward along the rotation axis. The result? Twin jets that shoot in opposite directions, punching through the surrounding plasma like lightning bolts through fog. These jets don't last long, seconds at most, but in that brief window, they release as much energy as an entire galaxy emits in years. To a distant observer, this looks like a short gamma-ray burst, one of the most intense flashes in the universe. For decades, astronomers thought such bursts only came from distant massive explosions. Now we know some are born right here in our galaxy, whenever a neutron star dies quietly but violently. If the Black Widow pulsar ever collapses, this is the fate waiting for it. The instant it crosses the Tolman-Oppenheimer-Volkoff limit, its dense interior will implode, and its rotational energy, all those hundreds of revolutions per second, will transfer into a final, narrow beam of destruction. The surrounding accretion disk, still filled with the last gas stolen from its companion, will funnel the outflow into two razor-thin jets blasting out of the poles. For a few heartbeats of cosmic time, it will be one of the brightest objects in the Milky Way. The jets themselves are composed of electrons, positrons, and magnetic fields moving so close to light speed that they generate intense radiation. As they interact with interstellar gas, they produce gamma rays, X-rays, and afterglows detectable across multiple wavelengths. These afterglows can last for hours, fading as the shockwave expands and cools. NASA's Fermi and Swift satellites routinely detect such events, sometimes faint, sometimes blinding, and each one may represent the silent death of a neutron star somewhere across the cosmos. The exact way that jets form is still one of the biggest puzzles in science. To do the process, the magnetic strength, spin, and accretion flow must all be perfectly balanced. There isn't enough magnetic field for a jet to form. Too much, and the disk won't be able to eat well. The sweet spot, which is where the most energy is extracted, might only last a few milliseconds. The dying star will either leave a whisper or a scream behind at that very moment. Simulations show that the faster a neutron star spins before collapse, the stronger and narrower the resulting jets become. That means objects like the Black Widow, spinning hundreds of times per second, are perfect candidates for creating these bursts. It's a dangerous paradox. The spin that kept it stable for millions of years also ensures its final moments will be cataclysmic. These jets also leave behind a more subtle legacy. They change the places they land. The plasma that is ejected cuts holes through nearby gas, which squeezes it and starts the formation of new stars. It could be said that every neutron star that dies helps make new stars. Destruction and production are the same thing. Some scientists believe that many of the strange bright gamma-ray flashes we see in galaxies far away are echoes of this process, dense objects dying and giving birth to light in the dark. For all their violence, relativistic jets don't last long enough to pose a danger to us unless they're pointed directly at Earth. The odds of that are minuscule. Even so, their energy output is staggering. A single jet could sterilize everything within dozens of light years if it struck head-on. That's one reason NASA monitors nearby pulsars so closely, just in case one of them transitions into this brief, lethal phase. Beam geometry. Are we in line? We think of pulsars as having flashes that happen at regular times, like a cosmic strobe. But here's the catch. We can only see those lights because the beam hits Earth. When you look at the star from a different angle, it goes out of sight, but it's still there, spinning in quiet. Everything we know about pulsars comes from this geometry, how exactly the beam, the spin axis, and our world are lined up. And when it comes to something as unstable as the Black Widow pulsar, that shape could mean the difference between seeing history happen and missing it. A pulsar's beams originate from its magnetic poles, not its physical poles. Because its magnetic field is misaligned with its rotation axis, each turn sends two beams sweeping across space like a lighthouse lamp cutting through fog. The angle between those axes, called the magnetic inclination angle, can range from just a few degrees to nearly 90. If the beam crosses Earth's line of sight, we see regular pulses. If it doesn't, the pulsar remains invisible, even though it still spins and emits radiation in every direction. That's one reason pulsars seem to turn on or off in the data. When a neutron star glitches or processes, slowly wobbling due to changes in its crust, its beam can drift slightly. A few degrees of movement are enough to shift its radiation away from our telescopes. From our perspective, it vanishes, even though nothing physically changed. Some astronomers suspect that many missing pulsars didn't die at all. Their beams just stopped pointing our way. The Black Widow pulsar's beam shape is one of the most sophisticated. Due to relativistic effects, its very fast spin changes its magnetic field, making it flatter and more twisted. Light may not come out in simple cones, but rather in fan-shaped sheets that move around over time. It's possible that each pulse we see here on Earth is just a small part of a much bigger pattern of emissions, a flicker from a single bright spot in a spinning storm. From above, the beams wouldn't look like straight lines. Instead, they'd look like tangled ribbons that are twisting because of gravity and spinning. This distortion matters because it affects how we measure the pulsar's properties. The apparent brightness, timing precision, and even the estimated mass all depend on how the beam crosses our viewpoint. When NASA's Fermi and NICER observatories track the Black Widow's radio and X-ray pulses, they must account for these geometric quirks. A beam hitting Earth dead-on looks brighter and more stable than one grazing the edge of our line of sight. Misjudge the geometry and you could miscalculate the pulsar's rotation rate or assume a change that isn't real. At 707 rotations per second, the Black Widow's equator moves at a significant fraction of the speed of light. That motion compresses the radiation ahead of its spin and dims the light behind it, much like the Doppler effect shifts the pitch of a passing siren. This means the beam isn't symmetrical. It's biased toward the direction of motion. If Earth happens to lie within that narrow zone, we see stronger, sharper pulses. If we're slightly outside it, the pulsar might appear weaker or erratic, even though it's performing exactly the same way. Understanding this geometry is more than just a technical exercise. It's the key to knowing whether we'd ever witness the Black Widow's final act. When, not if, it collapses, the first clues may come from a change in pulse alignment. As the pulsar's structure destabilizes, its magnetic axis could shift abruptly. A few milliseconds before the end, the beams might flicker or drift, warning us that the collapse has begun. But if Earth isn't within that beam path when it happens, we'd see nothing. The pulses would just stop, and we'd never know whether they ended from physics or perspective. Safe distances inside the Milky Way. It's about 100,000 light-years across, which is pretty big, but when you're talking about neutron stars, even that size seems too small. These things don't just go off like fireworks and disappear. They stay around, spinning and sending out dangerous energy over long lengths that are hard to imagine. The good news is that most of them are too far away to hurt Earth. There is a catch. Far enough isn't really that far away. A pulsar or magnetar doesn't have to be close to us to be dangerous. It only needs to be facing the wrong way. Astronomers have done the math, and the safe distance depends entirely on what kind of outburst you're talking about. A normal pulsar beam, harmless, even at a few hundred light-years. A magnetar flare like the 2004 Sagittarius event, that's different. A similar explosion within about 10 light-years could strip Earth's ozone layer in seconds, flooding the surface with lethal ultraviolet light. A distance of 40 light-years might still trigger climate shifts or radiation spikes detectable at ground level. Anything closer than 5 light-years, and the upper atmosphere could collapse entirely, ending life as we know it. That sounds terrifying, but in practice, we're safe. The nearest known magnetar, XTE J0952-0607, sits about 8,000 light-years away. Even the closest pulsars are hundreds of light-years out, far beyond the danger zone. And while the Milky Way hosts millions of dead stars, only a few dozen active magnetars have been detected, most clustered toward the galactic center. Our solar system, sitting quietly in one of the outer spiral arms, is in a remarkably peaceful neighborhood. Space agencies routinely map potential high-energy threats within the galaxy, not out of fear, but out of curiosity. When a neutron star flares, its radiation spreads outward in cones or beams, narrowing with distance. The chance of one aligning perfectly with Earth is small, roughly 1 in a million. But in a galaxy of 200 billion stars, 1,000,000 to 1 chance still means a few could theoretically happen. That's why NASA, ESA, and observatories like Fermi and Swift continuously scan the sky for sudden X-ray and gamma-ray spikes. Every unexpected flash could be another magnetar losing its temper somewhere in the Milky Way. There's a comforting scale to these distances. Light itself takes years to cross them, meaning anything dangerous has already happened thousands of years ago. And if the radiation hasn't hit us yet, it means the beam's not pointed our way. For instance, if the Black Widow pulsar were to collapse into a black hole tomorrow, we wouldn't see or feel the effects for 14,000 years. It's a built-in delay that turns cosmic danger into ancient history by the time it reaches us. Even so, astronomers like to test worst-case scenarios. Suppose a pulsar with the energy output of the Black Widow existed within 100 light-years, and its beam happened to cross Earth. The results would depend on the energy frequency. Radio pulses, we'd barely notice. X-rays and gamma rays, that's another story. The radiation would ionize the atmosphere, disrupting satellites, frying electronics, and flooding the surface with enough energy to sterilize entire ecosystems. It wouldn't destroy the planet, but it would make it uninhabitable. Fortunately, there's no sign of any such object anywhere near us. Not now, not in the foreseeable future. Where neutron stars do influence us is through their cosmic rays, charged particles accelerated by their magnetic fields and jets. These particles travel throughout the galaxy, occasionally reaching Earth. They're part of the constant cosmic radiation that hits our atmosphere, producing harmless auroras and secondary particles that scientists detect with ground-based observatories. The dose is tiny, a reminder that while we live in a galaxy filled with violent remnants, we're buffered by space itself. The greater point is that the safe distance isn't just about us. It tells us where in the galaxy life can survive. This area is known as the Galactic Habitable Zone by astronomers. It is a place where radiation levels are low enough for planets to be able to support complex chemistry. Supernovae, black holes, and magnetars are all around you if you get too close to the heart of the galaxy. There aren't enough heavy elements out there, and the planets are too far away to be hard. Our solar system is about 27,000 light-years from the center of the galaxy, which is far enough from chaos to be safe, close enough to metals to be safe, and far enough from the center to be safe from the magnetic field. Why continuous monitoring actually matters. Scientists aren't joking when they say that NASA watches the Black Widow pulsar 24 hours a day. Telescopes, monitors, and satellites are always looking for its signs all over the world and in space. The aim of all of them is the same: to catch a change. Some are tuned to radio waves, while others are tuned to X-rays or gamma rays. Because an object this unstable could have experienced a collapse, a flare, or the first known change of a neutron star into a black hole. A single missed pulse, a fractional dimming, or a shift in spin could be proof of this. The idea of constant observation might sound excessive, but in astrophysics, timing is everything. A pulsar's rhythm acts like a cosmic clock, ticking every few milliseconds with astonishing precision. If that rhythm shifts, it tells scientists something fundamental has changed in the star's structure. The Black Widow's timing is monitored to within a few microseconds by an international network of observatories. NASA's NICA on the International Space Station, Fermi, Chandra, Meerkat in South Africa, and the Green Bank Telescope in West Virginia. Together, they form a global surveillance system for the universe's most volatile objects. We've seen supernovae, gamma-ray bursts, and neutron star collisions, but we've never watched a pulsar cross the line into a black hole in real time. We know the theory, we've modeled the math, but we've never caught it in the act. If the Black Widow is as massive and unstable as data suggests, it's one of the few candidates where this could happen within our observational window. Maybe not in our lifetime, but possibly within the lifespan of our technology. Missing even a few seconds of that moment would mean losing the chance to witness one of the most important transitions in astrophysics. Continuous monitoring isn't just about waiting for a collapse, though. It's also how scientists test the limits of physics every single day. Pulsars are perfect laboratories for general relativity. Their extreme gravity warps time, bending the space around them so much that even their pulses arrive slightly delayed when passing near massive bodies. By tracking those delays, researchers can measure the curvature of space-time itself. They can detect the presence of unseen companions, measure gravitational waves, and even test how stable the laws of physics are under the most punishing conditions. For example, by studying the Black Widow's pulse timing, NASA can map the structure of its binary orbit with incredible accuracy. When the companion star moves between us and the pulsar, its gravity slightly alters the path of the pulses. That effect, known as Shapiro delay, allows astronomers to calculate the exact mass of both objects and confirm whether the pulsar is creeping closer to the Tolman-Oppenheimer-Volkoff limit. Those tiny timing fluctuations are like fingerprints of the star's internal stress, showing how close it is to failure. Constant observation is also a way to protect against fake fears. Space is full of noise, like background radiation, solar flares, and influence from other galaxies. If an observatory finds a strange signal or a pulse that isn't there, devices all over the world check the same locations right away. If more than one system backs it up, it's not noise, it's truth. This real-time network checks that NASA is telling the truth when they say that a pulsar has changed. The practical benefits extend beyond astrophysics. Pulsars are so precise that their signals are now being used for deep space navigation. The XNAV system, currently tested aboard the ISS, works like a galactic GPS. By comparing the arrival times of known pulsars, including the Black Widow, spacecraft can determine their position anywhere in the galaxy without relying on Earth. But for that to work, those pulsars must be tracked constantly to update timing models. A single unmonitored drift could throw off navigation accuracy by thousands of kilometers. In short, NASA's vigilance isn't just curiosity, it's calibration for future exploration. NASA watches. NICER Fermi Swift rolls. To understand how NASA keeps an eye on something 14,000 light-years away, think of a cosmic relay race. There is a network of telescopes in orbit around the Sun, each intended to pick up a different type of light, and data is sent between them almost in real time. NICER, Fermi, and Swift are the three tools that are at the center of that system and are in charge of keeping an eye on neutron stars. They let us know at all times what the Black Widow pulsar is doing, like how fast it's turning, how hot it is, and whether it's getting closer and closer to falling apart. Let's start with NICER, the Neutron Star Interior Composition Explorer. Mounted on the outside of the International Space Station, it looks like a cluster of small silver tubes pointed into space. Each one houses an X-ray detector so sensitive it can count individual photons. NICER's mission is to take the pulse of neutron stars, literally. It measures the timing and brightness of their X-ray flashes down to microseconds. That precision allows scientists to map how matter behaves inside these ultra-dense stars, testing equations of state that describe how pressure and density interact under extreme gravity. In the Black Widow's case, NICER is the tool that tracks its heartbeat with atomic accuracy. Every pulse is logged, every slight delay or acceleration catalogued. NICER's data tells scientists whether the pulsar is stable or slipping. If the timing starts to drift even slightly, it could mean the crust is fracturing or the rotation rate is changing due to accretion. Because NICER is on the ISS, it orbits Earth every 90 minutes, giving it multiple chances per day to observe the same object from different positions. That allows researchers to isolate background interference and refine the data with unmatched clarity. It's not glamorous, but it's how astrophysics builds certainty, second by second, pulse by pulse. Then there's Fermi, NASA's all-sky sentinel. Officially called the Fermi Gamma Ray Space Telescope, it's the galaxy's constant listener for high-energy radiation. Where NICER focuses on precision, Fermi is about coverage. It scans the entire sky every 3 hours, looking for sudden spikes, flares, bursts, or anomalies that could signal a starquake or magnetar eruption. Fermi's instruments can detect photons with energies millions of times greater than visible light, the kind produced when particles are accelerated to near-light speed by intense magnetic fields. When Fermi catches something unusual, a brief gamma-ray flash for instance, it immediately alerts the Global Astronomy Network through the Gamma Ray Coordinates Network, GCN. Within seconds, observatories around the world turn their telescopes toward the source. That's how the 2004 Sagittarius magnetar flare was detected. And it's how NASA hopes to catch the Black Widow's potential collapse if it ever happens. If the pulsar emits a sudden burst or its pulses cut off mid-sequence, Fermi will be the first to notice. The Swift spaceship, on the other hand, was made to be fast and adaptable. Fermi looks up at the whole sky. NICER stares very closely, but Swift can turn. It has both a wide-field gamma-ray monitor and a narrow-field X-ray camera, so it can quickly find a burst and then zoom in for more information. It's the first thing that comes to mind when you think of high-energy science. Scientists get a lot of different kinds of data from Swift's ability to respond to Fermi's alerts. For example, Swift can quickly find gamma rays, Fermi can do detailed X-ray imaging, and NICER can do exact time analysis. The three devices work together to form a triangle that lets scientists see every part of a pulsar's behavior, from small quivers to huge flares. Together, these missions have turned pulsar monitoring into something resembling a live broadcast. When Fermi sees a spike, Swift refines it, and NICER confirms it. Data is relayed in real time to NASA's Goddard Space Flight Center and distributed to universities worldwide. In some cases, automated algorithms flag anomalies within minutes, prompting human teams to initiate focused observation campaigns. It's like having the universe under constant surveillance, not out of paranoia, but out of scientific vigilance. Ground support, LOFAR green bank timing. NASA's space telescopes are very powerful, but the real work that has been done on pulsars is still done here on Earth. Huge fields of radio dishes are spread out across countries. These are machines that are so sensitive that they can pick up a signal from the moon that is weaker than a phone call. The people on the ground who listen, track, and time each pulse with obsessive accuracy are the hidden stars of pulsar research. At the same time that instruments in space catch bursts of high energy, grids on Earth keep the beat going. And rhythm is very important when you're looking at a star that could fall apart at any time. The most famous of these ground stations is the Green Bank Telescope in West Virginia, a single massive radio dish stretching 100 meters across, the largest fully steerable one on the planet. It sits in the middle of the National Radio Quiet Zone, where cell signals, Wi-Fi, and even car ignitions are restricted to keep interference out. Every day, Green Bank locks onto targets like the Black Widow pulsar and listens for those faint, rhythmic radio pulses. The telescope's receivers can measure arrival times to within a few millionths of a second, tracking subtle changes that could reveal shifts in the pulsar's orbit, spin, or magnetism. When scientists talk about timing, this is what they mean: collecting years' worth of pulses and measuring how precisely they arrive. If the Black Widow slows by even a billionth of a second, the timing model will pick it up. That data feeds into international collaborations like the Nanograv project, which uses pulsars as natural detectors for gravitational waves, ripples in spacetime from distant black hole mergers. By comparing the arrival times from dozens of pulsars spread across the sky, researchers can spot tiny distortions in the Earth pulsar distance caused by passing gravitational waves. The Black Widow's consistency makes it one of the more valuable pulsars in this experiment, a galactic metronome helping to listen for cosmic symphonies. Across the Atlantic, the LOFAR, Low Frequency Array Network, stretches across Europe, with stations in the Netherlands, Germany, Poland, France, and the UK. Instead of one big dish, LOFAR uses thousands of small antennas spread over a massive area, all digitally linked to form a single giant telescope. It listens in the low-frequency radio bands, catching the deep, rolling tones of pulsars that higher-frequency telescopes might miss. For the Black Widow, LOFAR provides crucial coverage during its quieter phases. Those stretches when its high-energy pulses fade and only the faintest radio heartbeat remains. Together, Greenbank and LOFAR form a kind of stereo system for the galaxy. Greenbank hears the higher pitches, crisp, fast pulses in the gigahertz range. LOFAR picks up the bass, the slow, rumbling undertones at lower frequencies. Combine the two, and scientists can reconstruct the pulsar's full emission profile, like mixing tracks in a cosmic recording studio. That layered data reveals how the star's magnetic field interacts with its plasma environment, how its beams evolve, and whether subtle changes in pulse shape might hint at an approaching instability. It's amazing how precise this work has to be. Atomic clocks and GPS time signals that are accurate to within nanoseconds are used by both ground arrays to keep all readings in sync. Observatories must make sure that the timestamps of each pulse line up properly, or else the data can't be put together. Even Earth's atmosphere and regional drift are taken into account. Software changes based on how much the planet's spin or air moisture slows down radio waves. This gives scientists a level of accuracy that is on par with particle physics, but they are measuring the heartbeat of a star 14,000 light-years away instead of collisions in a lab. This ground network also acts as a global early warning system. When NASA's satellites detect a flare or sudden X-ray spike, Greenbank, LOFAR, and other radio telescopes like Parkes in Australia or Effelsberg in Germany pivot toward the source. Within minutes, the entire network is recording. If the pulses vanish, the world will know almost immediately. That coordination isn't just impressive, it's essential. The universe doesn't wait for anyone, and the first team to capture the signature of a pulsar collapsing into a black hole will make history. Gravitational wave fingerprints of collapse. Every big event in the universe leaves an echo, which is a ripple in space-time. Gravitational waves are tiny distortions that stretch and squeeze space as they pass through it. They are made when black holes join or neutron stars crash into each other. In 2015, humans found them for the first time, proving Einstein's statement from 100 years earlier. But there's something else we've never heard of: a neutron star slowly falling apart into a black hole. When the Black Widow pulsar goes over that line, it won't go out with the light. A weak pulse through the world will mark its end, which could change what we think we know about how stars die. Gravitational waves are unlike any other signal. They don't travel through space like light or sound. They are space, moving. When a massive object changes shape rapidly, especially in an asymmetric way, it disturbs space-time itself. The result is a wave that travels outward at the speed of light, carrying information about the motion that created it. For merging black holes, those waves come from the violent coalescence of two enormous gravitational wells. For collapsing neutron stars, they'd come from the sudden loss of symmetry as the star's structure fails. Visualize the Black Widow in its last moments. It's spinning hundreds of times per second, and the force of centrifugal force is making it smooth out into a sphere. As accretion adds mass, the core of the galaxy gets smaller, which throws off the balance between gravity and neutron pressure. The resistance then gives way in an instant. It's not a perfectly even breakdown as the top layers fall in. As the star falls apart, its shape twists a little. This uneven motion causes a tremor in the universe, which is called a gravitational wave. It carries the signal of a dead star's last breath. These waves would be faint, far weaker than those from black hole mergers, but not undetectable. Instruments like LIGO, Virgo, CAGRA, and the upcoming Einstein telescope are sensitive enough to catch them if they occur nearby, within perhaps 10 or 20,000 light-years. The Black Widow fits that range. If it were to collapse, We could, for the first time, detect the exact instant a neutron star becomes a black hole, not through light, but through space itself moving. The shape of the wave, its fingerprint, would tell us everything. Unlike the clean chirp of a binary merger, a collapse would produce a quick, chaotic pulse followed by silence. The waveform would start with a sharp peak as the crust caves in, followed by a damped oscillation as the remaining matter falls through the event horizon. Its frequency would lie somewhere in the kilohertz range, corresponding to the neutron star's final spin rate. A perfect match between timing data from NICER or Fermi and a gravitational wave spike from LIGO would confirm beyond doubt that we'd just witnessed stellar collapse in real time. This is why continuous monitoring matters so much. Light and gravity must be observed together to understand the full picture. Light tells us when the star's pulses stop. Gravitational waves tell us why. Together, they'd give the first complete record of a black hole's birth. Astrophysicists call this kind of observation multi-messenger astronomy, and it's already transformed our understanding of the universe. When the neutron-star merger GW170817 was detected in both gravitational waves and electromagnetic radiation, it confirmed that such events create heavy elements like gold and platinum. A future detection of a solitary pulsar's collapse would do the same for black hole formation, confirming, once and for all, how the line between matter and nothingness is crossed. There's an additional possibility that is quite odd. Neutrons break apart into free quarks in a state called quark deconfinement, and the Black Widow's core disappears into the singularity. If the core doesn't collapse all at once, it might go through this state for a short time. There could be a unique double-peaked gravity signal from that process. One wave would come from the first collapse into a quark star, and the other would come from the end, collapse into a black hole. If we could find that pattern, it would mean we had seen a form of matter that has never been seen before in nature. It would be the step between nuclear matter and pure gravity. What LIGO Virgo Cagra could hear. In September 2015, the first gravitational wave signal hit Earth. It was a faint rising chirp that went through our planet without being noticed by anyone but a few scientists, who were looking at a computer in shock. That sound was made by two black holes colliding more than 1 billion light-years away. As of now, dozens of these cosmic songs have been caught by instruments like LIGO, Virgo, and Cagra. These are collisions, spirals, and crashes that bend space itself. Some sounds they've heard but never caught are the tremors of a single neutron star dying as it falls apart into a black hole. And this is what those sites might hear if the Black Widow pulsar hits the Earth. Unlike the long, sweeping signals of binary mergers, a pulsar collapse would produce a short, asymmetric burst of gravitational waves, a sharp, abrupt vibration lasting only milliseconds. It wouldn't crescendo or fade. It would strike like a drumbeat, a single wavelet that shakes space-time and vanishes. Detecting something so brief demands extreme sensitivity. That's where the global trio of detectors comes in, each one designed to pick up movements smaller than a proton's width. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses two 4-kilometer-long tunnels, one in Hanford, Washington, and another in Livingston, Louisiana. Each tunnel contains a laser beam bouncing between mirrors with perfect precision. When a gravitational wave passes through, it stretches one arm slightly while compressing the other. The difference, smaller than a fraction of an atom, produces a telltale interference pattern. That's the chirp we hear translated into sound. Virgo in Italy operates on the same principle, and Cagra in Japan adds a twist. It's built underground and cooled to cryogenic temperatures to reduce noise. Together, the three form an Earth-sized observatory, triangulating any gravitational event with astonishing accuracy. Think about what would happen if the Black Widow fell. The pulsar's core breaks off 14,000 light-years away, deep in the halo of the Milky Way. It stops spinning all of a sudden after 707 turns per second as the rock caves in. The fall isn't even because of the fast spin and magnetic field. That difference in symmetry is very important. It's what makes gravity waves. The distortion races through space-time at the speed of light and spreads outward in a fraction of a millisecond. The wave's amplitude will have dropped to about 1022 by the time it gets to Earth, but that's exactly what LIGO and Virgo are designed to see. If such a signal arrived, the network's computers would immediately cross-check it with other detectors. A near-simultaneous blip in all three would confirm it's not local noise, but a real cosmic event. Within seconds, automated alerts would go out to telescopes worldwide. NICA and Fermi would swivel to the source. If the pulses from the Black Widow stop at the same time, the evidence would be undeniable. We just watched a neutron star die. The waveform would tell the story. A collapse signal is expected to start around 1 kHz, roughly the frequency of a dog whistle, and then decay almost instantly. Its exact shape would depend on how the star's interior fails. A sudden sharp peak might indicate a clean implosion, while a more complex double structure could hint at an intermediate stage, perhaps a brief quark star phase before total collapse. The damping tail, fading over milliseconds, would show how the new black hole settled into equilibrium. In essence, the universe would be humming the blueprint of its own physics. But gravitational wave astronomy isn't just about the drama of detection, it's about precision. By measuring the wave's amplitude and duration, scientists could estimate the exact mass and spin of the newborn black hole. If the numbers line up with the Black Widow's known properties, we'd confirm that nature can push neutron stars right up to the Tolman-Oppenheimer-Volkoff limit before they fold. That alone would tighten the boundaries of nuclear physics, telling us exactly how much pressure neutron matter can endure. If the collapse triggers any electromagnetic emission, a brief X-ray or gamma-ray pulse, and that light reaches us alongside the gravitational wave, it would give scientists a direct comparison of arrival times. Since both travel at light speed, any delay would test Einstein's theory with unprecedented precision. If gravity and light arrive even a microsecond apart, that could hint at new physics, perhaps the influence of dark matter or hidden dimensions affecting one, but not the other. Glitches and spin-downs. As warnings. A pulsar is like a clock for most of its life. Scientists use them as cosmic metronomes to measure time all over the galaxy because the pulses they make are so stable. But every once in a while, that perfect beat falls apart. The beat jumps. It's only a fraction of a millisecond that the pulse comes in early or late. Anyone who isn't taught can see it as nothing. It means a lot to scientists. For a star like the Black Widow pulsar, that flash could be the only sign that something very wrong has happened inside. It's called a glitch. A glitch is essentially a starquake in motion, a sudden change in the pulsar's spin rate caused by internal stress. Neutron stars aren't perfectly rigid. Their outer crusts are solid iron, but beneath that lies a superfluid ocean of neutrons swirling in quantum vortices. These vortices carry most of the star's angular momentum, and over time the crust and the fluid core can fall out of sync. The crust spins slightly slower, dragging behind the superfluid interior. Eventually the stress builds until the two layers violently reconnect. When that happens, angular momentum transfers suddenly from the core to the crust, causing the whole star to speed up ever so slightly, a tiny twitch in its rotation. The first time scientists saw this was in 1969, when the Vela pulsar, another neutron star in our galaxy, unexpectedly jumped in spin frequency. Since then, hundreds of glitches have been observed across dozens of pulsars. Each one is unique, a fingerprint of the internal structure we can't see directly. And every time a pulsar glitches, it gives researchers a rare look into the physics of matter under unimaginable pressure. For the Black Widow pulsar, which spins 707 times per second, a glitch would be monumental. At those speeds, even a fractional change would release staggering amounts of energy. If its rotation increased by just 1 part in a billion, the mechanical energy released could equal the power output of our sun for days. The surface would quake, the magnetic field might shift, and radiation patterns could alter. In the data, this would appear as a sudden irregularity in pulse timing, a hiccup in the cosmic heartbeat. NASA's nicer and ground-based arrays like Green Bank monitor for exactly that kind of signature, because it could mark the first domino falling toward collapse. But glitches aren't always accelerations. Sometimes, pulsars experience the opposite, a gradual spin down, a slowing of their rotation over time. This happens because pulsars lose energy through radiation and magnetic braking. Each beam of light or radio emission carries away angular momentum, like a figure skater slowly extending her arms. Most pulsars spin down predictably, losing a tiny fraction of their speed every year. For the Black Widow, however, the balance is unstable. Accretion from its dying companion can temporarily spin it up, while radiation tries to slow it down. The result is a tug-of-war between feeding and fatigue. The ratio of spin-up to spin-down events is very important to scientists because it shows how close the pulsar is to losing its structure. If spin-down takes over, it means that the pulsar's rotating support is getting weaker. If there is no centrifugal force, gravity can pull things in more easily. If mass keeps building up even though spinning slows down, the chance of failure goes through the roof. This is why time problems aren't just interesting, they're a sign of something wrong. If the beat changes, it could mean that the star's core is moving around. To catch these changes, observatories maintain long-term timing databases, some stretching back decades. Algorithms compare each new pulse to years of previous data, searching for deviations smaller than a microsecond. When one appears, teams rush to cross-check with other instruments. Did Fermi detect a burst? Did Swift see an X-ray flare? If not, it's a glitch, an internal adjustment, not an explosion. If yes, something bigger may be underway. Accretion rates, the real ticking clock. The Black Widow pulsar is like a bomb. Its trigger is mass, not time. It feeds on a small amount of gas pulled from its dying partner every second, and that flow controls everything. If you don't give it enough, the star will spin down and slowly disappear. If there is too much, it will fall apart. This flow is known as the accretion rate in astronomy. In this case, it's the real timer that shows how long this neutron star can last before it collapses under its own weight. Think of accretion as a kind of celestial siphon to understand why it is so dangerous. The partner is a white dwarf that is less than 2% of the mass of the Sun. It orbits so close that its outer atmosphere spills over the edge of its gravity field. The gas doesn't fall straight into the pulsar. Instead, it swirls in and makes an X-ray emitting hot ring. The friction in that ring heats the plasma to millions of degrees, and as the gas falls toward the neutron star, it gives it mass and rotational momentum. The gravity noose gets tighter as each atom adds to the weight that is pulling on the core. At first, accretion stabilizes the system. The extra spin it provides helps counteract gravity, allowing the pulsar to maintain balance. But as the accretion rate continues, that benefit turns to poison. The neutron star's rotation can't increase indefinitely. There's a physical limit called the mass-shedding threshold, the point where centrifugal force at the equator equals gravity's pull. Once it reaches that, any further gain in mass doesn't increase spin, it just adds pressure. And in an object already near the Tolman-Oppenheimer-Volkoff limit, that's catastrophic. NASA and the European Space Agency estimate the Black Widow pulsar's accretion rate at about 10 to the power of -10 solar masses per year, a tiny figure by human standards, yet massive on cosmic scales. At that pace, the pulsar adds roughly the mass of Mount Everest every few days. Over hundreds of thousands of years, that steady feeding becomes dangerous. The only question is whether the star hits its breaking point first, collapsing under its own weight, or runs out of material to consume before it gets there. Astronomers track the accretion rate indirectly through X-ray brightness and changes in the companion's light curve. When the pulsar's radiation heats the white dwarf's day side, the escaping gas produces subtle color shifts that can be modeled to estimate how much matter is being lost. In recent years, that data has shown something startling. The rate isn't constant. It fluctuates in cycles, with bursts of intense feeding followed by quieter phases. During active periods, the pulsar's accretion rate can spike tenfold, accelerating its mass gain dramatically. Those feeding frenzies might only last months, but over millennia, they add up. This dynamic is what makes systems like the Black Widow so unpredictable. They're not steady clocks, they're chaotic ecosystems. The pulsar's intense radiation blasts away some of the infalling material, creating a feedback loop that throttles its own meal. Too much radiation, and the companion star's outer layers are vaporized faster than gravity can feed them in. Too little, and the gas flows freely, increasing the pulsar's mass dangerously fast. The balance swings constantly, like a pendulum between survival and annihilation. At certain thresholds, accretion becomes self-sustaining. When enough gas accumulates in the disk, it heats until the viscosity spikes, allowing more material to plunge inward. These accretion outbursts unleash massive bursts of X-rays as the gas slams into the neutron star's surface. Observatories like SWIFT and XMMM Newton have recorded such flares, each one a sign that the system has entered a temporary feeding surge. The afterglow from these bursts often fades within hours, but the mass they deliver stays forever. Small increments on the cosmic scale, but cumulative steps toward collapse. Accretion also drags on the pulsar's spin. As matter piles on, the distribution of mass changes, shifting the moment of inertia. This can slightly alter the pulsar's timing, producing microsecond-scale irregularities detectable by instruments like NICER and Green Bank. Those fluctuations, though tiny, may be the most reliable early indicators that the star's balance is slipping. If astronomers notice the pulses lengthening, the spin slowing even as accretion remains high, that's the signal that rotation is losing the fight against gravity. The most terrifying element is that the last step could come on quickly. The neutron star will almost certainly crash as soon as its core density goes over a certain point. This could be caused by one last burst of accretion. It will not get darker over time, and there will be no clear timer. The pulses will stop right away. What's left will be hidden when the light goes out. In less than a second, the star's whole magnetic structure will be sucked up. Magnetic fields that shred atoms. People only talk about gravity when they talk about neutron stars, which are the forces that crush suns into bodies the size of cities. But these things aren't really scary because of gravity. These things have magnetic fields that bend space, stretch atoms, and change the rules of matter. That field is trillions of times stronger in the Black Widow pulsar than it is on Earth. It's so strong that it can break up atoms before they even get to the surface. It's hard to understand how magnetism works at this level, where electrons are pushed into straight lines and light bends to follow. At the surface of a neutron star, the magnetic field reaches between 10 to the power of 12 and 10 to the power of 13 Gauss. For comparison, the strongest magnets ever built on Earth barely touch a few 100,000 Gauss before they rip themselves apart. The Black Widow pulsar's field is so intense that even from 1,000 kilometers away, it could wipe every credit card strip, hard drive, and radio signal on the planet. Any closer, and it wouldn't just destroy electronics, it would begin to reshape the atoms themselves. Here's why. Under normal conditions, an atom's electrons orbit the nucleus in a soft, three-dimensional cloud, balanced between the pull of electromagnetism and quantum uncertainty. But once the magnetic field climbs above about 10 to the power of 9 Gauss, that balance collapses. The field takes over, crushing the electron cloud into a narrow cylinder aligned with the magnetic axis. In the environment of the Black Widow pulsar, the effect is extreme. Atoms are stretched hundreds of times their normal length, and the familiar electromagnetic forces that define ordinary matter no longer behave the same. At that point, even the structure of atoms is rewritten. Physicists call this Landau quantization, and it's one of the strangest consequences of quantum mechanics meeting astrophysics. In essence, electrons in such a strong magnetic field can only occupy certain discrete energy levels called Landau levels. The higher the field strength, the fewer options an electron has. Near a neutron star, it's not an orbiting particle anymore. It's trapped in a one-dimensional energy ladder. The result is atomic matter that behaves more like a metallic solid than a gas, The surface of the pulsar is literally made of compressed, magnetized iron frozen into quantum alignment. This extreme magnetism doesn't just warp matter, it reshapes light itself. In fields above 10 to the power of 12 Gauss, photons interact with the magnetic field in a process called vacuum birefringence. Normally, light travels straight through empty space, but here the vacuum behaves like a crystal, splitting light into two polarizations that travel at slightly different speeds. When astronomers use X-ray polarimeters to study pulsars, they can see this effect directly. Light leaving the star is twisted, polarized, and filtered by magnetism before it even reaches us. In a system like the Black Widow, this magnetic power is constantly at war with gravity and radiation. The field guides incoming plasma from the accretion disk along invisible funnels toward the magnetic poles. As the gas races down these funnels, it crashes into the surface at nearly a third of the speed of light, releasing X-rays in bursts called hotspots. The intense field prevents the plasma from spreading out, confining it to tiny patches only a few hundred meters wide. That's why pulsars shine in pulses. Each hotspot acts like a flashlight beam, sweeping across space as the star rotates. But magnetic fields this strong are not stable. They decay slowly over millions of years, releasing stress through reconnection events, sudden rearrangements of field lines that release huge bursts of energy. These events are responsible for smaller flares seen in both pulsars and magnetars. In the Black Widow's case, such reconnections might contribute to the faint but regular X-ray flickers detected by NASA's Chandra Observatory. Those are magnetic aftershocks, tiny reminders that even in apparent calm, the star's field is constantly shifting beneath the crust. If the Black Widow ever collapses into a black hole, that magnetic field won't simply vanish. It will be dragged inward and twisted around the newborn singularity. For a few seconds, the decaying field could create a pair of relativistic jets, the same kind of high-speed plasma beams seen after gamma-ray bursts. Then, like everything else, the field will disappear behind the event horizon, leaving only its gravitational fingerprint behind. The fact that we can see so much of this from so far away is amazing. Astronomers can get a good idea of the pulsar's magnetic field structure by looking at how X-rays and radio waves are polarized. This polarized light from neutron stars has already been found by instruments like IXPE, NASA's Imaging X-ray Polarimetry Explorer. This proves what scientists have thought for decades. The Black Widow's beam isn't just light, it's electricity that you can see. Pulsar planets, how any survive. If neutron stars are where the universe's big pieces fall apart, then planets going around one sounds like it can't be possible. A pulsar like the Black Widow is a spinning weapon that can destroy anything close with its strong radiation, magnetic storms, and high-energy particles. Still, some of these monsters have planets. There are real hard worlds that have survived in one of the most dangerous places ever found. It seems like a glitch in the code of astronomy every time scientists find one. The first hint came in 1992, when Alexander Wolszczan and Dale Frail detected faint rhythmic variations in the pulses of PSR J0952-0607. The pattern wasn't random noise, it was gravitational tugging from orbiting bodies. That single discovery gave us two firsts at once, the first confirmed exoplanets ever found, and the first proof that planets can orbit a pulsar. They weren't gas giants or icy comets either. They were dense, Earth-sized rocks moving in tight, eccentric orbits. Somehow, after a supernova obliterated their star, after radiation swept the region clean, new worlds emerged from the debris. How does that even happen? There are two main theories. The first says these planets are second-generation worlds, born from the ashes. When the massive progenitor star exploded, not all of its material escaped. Some of it fell back, forming a disk of heavy elements around the newborn neutron star. Over millions of years, that debris cooled and coalesced into rocky planets. The second theory is darker. They could be remnants of a shredded companion. If the pulsar once had a binary partner, tidal forces might have torn it apart, scattering its remains into orbit and recombining them into new bodies. Either way, these planets are survivors, forged not in starlight but in catastrophe. A pulsar system doesn't offer much hospitality. The radiation environment is lethal. Constant X-rays, gamma rays, and charged particles pour out from the magnetic poles. A planet's surface would be bombarded with energy millions of times higher than anything near Earth. No atmosphere could last. Even rock and metal would sputter under direct exposure. If any of these worlds have retained solid surfaces, they must be shielded by thick crusts, possibly with subsurface oceans or molten mantles. Life, at least as we know it, would be unthinkable. But physics doesn't forbid chemistry. Deep beneath the surface, insulated by kilometers of rock, exotic reactions might still occur, powered by the pulsar's relentless flux. The planets we found around pulsars tend to be oddly arranged. Their orbits are elliptical, tilted, and sometimes resonant, locked in gravitational dance steps that hint at chaotic origins. In PSR J0952-0607, for instance, two of the planets orbit in a near-exact 3:2 ratio, suggesting they migrated over time before settling into balance. Another system, PSR J2007+3120, hosts at least two massive bodies several times heavier than Earth, circling a pulsar that rotates 41 times per second. Their orbits stretch across millions of kilometers, yet remain stable, an improbable serenity in the middle of cosmic violence. Finding these worlds isn't easy. Pulsars are perfect clocks, and planets reveal themselves only by disturbing that precision. As a planet tugs on the star, it changes the arrival time of pulses by mere microseconds. To detect that, astronomers compare years of data, correcting for Earth's motion, solar interference, and even atmospheric delays. When a repeating pattern remains, it's proof that something is orbiting. Unlike most exoplanets discovered through dips in starlight, pulsar planets are found by their rhythm, tiny changes in the beat of a cosmic drum. The discovery of pulsar planets makes us wonder how many more are out there hiding. We've only found a few because most of them are very hard to spot. There are thousands of known pulsars, but only about 0.5% show clear signs of having planets in orbit around them. That could mean they're very uncommon, or that our methods don't find them. If future radio arrays like the Square Kilometre Array, SKA, reach their full sensitivity, they could find dozens more, showing a whole group of previously unknown solar systems after the end of the world. Natal kicks and rogue remnants. Neutron stars all start out their lives by exploding. A supernova is not a slow change, it's like a cosmic gun blast. When the center of a big star falls apart, the outer layers bounce back and tear apart at tens of thousands of kilometers per second. That uneven blast can give the neutron star that's left over something unexpected: a kick. These natal kicks send the bodies of dead stars hurtling through space like cosmic grenades. This is why so many pulsars go missing and end up far from where they were born. The speeds are mind-bending. Typical neutron stars shoot off at 400 to 1,000 kilometers per second, and a few record breakers exceed 1,500, fast enough to escape the Milky Way entirely. Imagine a collapsed star, just 20 kilometers across, racing faster than a bullet. These objects are tiny, dense and invisible without their radio pulses, yet they carry the kinetic energy of entire planets. Once launched, they drift across space for millions of years, glowing faintly as their rotation and magnetic fields gradually slow. The mechanism behind these kicks is still a mystery. The leading theory points to asymmetry in the supernova explosion itself. When a massive star implodes, the collapse doesn't occur evenly. Slight differences in temperature, magnetic fields, or neutrino emission between hemispheres can cause one side to explode harder than the other, giving the newborn neutron star a recoil velocity. Another possibility is binary disruption. If the star had a companion before it went supernova, the sudden loss of mass during the blast can unbalance the system, slinging both remnants in opposite directions. Either way, the result is the same: a lone neutron star speeding through the dark. The Black Widow pulsar likely began that way. Somewhere billions of years ago, its progenitor star detonated, flinging the new neutron star and its surviving companion into a distorted orbit. The fact that it still has a partner, even one that's now a stripped-down white dwarf, is remarkable. Many systems don't survive the blast. The binary tears apart, and the neutron star becomes a wanderer. Astronomers have catalogued dozens of these runaway pulsars, their motion traced by measuring the Doppler shift in their radio emissions, or the trail of ionized gas they leave behind. One of the fastest ever recorded, PSR J0952-0607, tears across space at about 1,100 kilometers per second. If it keeps that pace, it'll leave the galaxy in less than 25 million years, a literal escapee from the Milky Way's gravitational grip. Others move more slowly, but in weirder directions, some apparently ricocheting from multiple gravitational encounters before finding a steady path. The physics of these motions helps astronomers reconstruct the violent asymmetry of the original supernovae, like reading the trajectory of debris to understand an explosion you didn't witness. Natal kicks don't just scatter neutron stars, they shape the structure of the galaxy itself. Some of the high-speed remnants wind up in the galactic halo, where few stars exist. Others drift into intergalactic space, becoming the ultimate exiles. In fact, simulations suggest there could be billions of rogue neutron stars silently crossing the void between galaxies, invisible unless their magnetic poles happen to point our way. These ghosts don't emit much light, but they occasionally reveal themselves through microlensing, when their gravity briefly magnifies the light of background stars. Every once in a while, telescopes catch one of these flukes, a momentary brightening that hints at a compact traveler passing by unseen. For astronomers, these kicks create both headaches and opportunities. A fast-moving neutron star can escape detection entirely, spinning away before surveys ever notice it. But when tracked, its trajectory offers a rare laboratory for gravitational dynamics. By plotting its velocity and direction, scientists can trace back to its birthplace, often a now empty region of a supernova remnant. Some of those remnants still glow faintly in X-rays, confirming the link between explosion and exile. Each runaway pulsar is a living fossil of the galaxy's violent past. As for the Black Widow, it might still be moving. It might be slowly drifting through space with its partner. The speed isn't fast enough to escape, but it's fast enough that the system could move far away from where it started over billions of years. That's why some Black Widow pulsars look like they're alone, floating in parts of the Milky Way that are otherwise empty. They are wanderers who lived through chaos and now live quiet, damaging lives by themselves. Where millisecond pulsars live in clusters. You don't look in the galaxy ring where stars like our Sun live if you want to find the most extreme neutron stars in the Milky Way. These are the ones that spin the fastest, are packed in close together, and are the oldest survivors. You look in groups of globules. These are very old, round groups of stars that circle the Milky Way like shiny satellites. Each one has hundreds of thousands of suns packed into a place that is only a few dozen light-years wide, and pulsars do well in these busy star cities. Millisecond pulsars are the same type of very fast, recycled neutron star that the Black Widow is made of. They are born in groups. Globular clusters are special for one reason: density. In the core of a typical cluster, stars are so close that distances between them can be less than 1/10 of a light year, about the width of our solar system. Gravity keeps the cluster bound together, but inside, chaos reigns. Stellar encounters happen constantly. Binary systems form, break apart, and reform as stars exchange partners in gravitational interactions. It's like cosmic speed dating on repeat for billions of years. Those interactions are exactly what a neutron star needs to spin up into a millisecond pulsar. Here's how the process unfolds. A neutron star starts as the collapsed core of a massive star, probably born billions of years ago when the cluster itself was young. Over time, it encounters another star, often an ordinary red giant. If the two form a binary pair, the neutron star begins pulling in matter from its swollen companion. This accretion process transfers both mass and angular momentum, steadily increasing the neutron star's spin. After millions of years, the feeding ends. The donor star is stripped down to a white dwarf, and the neutron star, now spinning hundreds of times per second, shines as a millisecond pulsar. Clusters are full of these systems because they create ideal conditions for recycling old neutron stars. In the wider galaxy, the odds of such close encounters are nearly zero. The stars are simply too far apart. But in a cluster's dense core, every few thousand years, a neutron star might capture a new companion or replace an existing one. That's why astronomers often find dozens of pulsars in a single cluster. The record holder, Terzan 5, contains over 30 confirmed millisecond pulsars, each one a beacon of precision timing and extreme physics. Cluster pulsars often show signs of gravitational disturbance from their neighbors. Their pulse timing reveals tiny wobbles as nearby stars tug on their orbits. By studying these variations, astronomers can map the cluster's hidden mass distribution, including dark matter candidates and unseen black holes. In this way, millisecond pulsars act like GPS satellites for entire clusters, allowing researchers to track how gravity shapes these ancient systems. The surroundings are left over from when the world was young. Globe-shaped groups of galaxies formed more than 10 billion years ago, a long time before the spiral arms of the Milky Way formed. Some of the oldest stars known are in their halo as they circle the galaxy's halo like skeletons from a different time. They have millisecond pulsars inside them, which shows that star evolution never really stops, even in the oldest parts of space. Even though they were formed in explosions billions of years ago, these neutron stars are still alive. They spin, give off radiation, and time out the slow beats of history. The Black Widow pulsar isn't located in a cluster, but its evolutionary path matches what happens inside them. Many of its close cousins, like PSR J0952-0607 and PSR B1957+20, are thought to have been ejected from clusters during gravitational interactions. That would explain their current isolation. They began life in dense environments, gained companions, spun up, and were later flung out into open space. Once exiled, they continued feeding on their partners until only a faint white dwarf remained. In a sense, every Black Widow pulsar is a refugee from a cluster, carrying the memory of that crowded origin. Mapping hotspots on magnetocrusts. A magnetar is a neutron star with a magnetic field so strong that it can actually tear its own surface apart. If a pulsar is a precise engine, then a magnetar is that engine pushed to its limits. Magnetars glow slightly in X-rays when they are at their calmest. They get their power not from growth or spin, but from magnetic decay. In their worst moments, they explode in huge explosions that light up half the world. In the middle, scientists have found something very interesting: hotspots, which are glowing scars spread out on the crust. Each one is a mark of unimaginable stress below the surface. The outer layer of a magnetar isn't soft or gaseous like an ordinary star's. It's a crust of crystalline iron and neutron-rich nuclei, a sheet of solid matter just a kilometer thick, sitting atop a sea of superfluid neutrons. Through that crust, magnetic field lines thread upward from the interior, anchored like roots in a buried dynamo. But the field isn't uniform. It twists, tangles, and occasionally snaps. When it does, energy from the magnetic interior punches through the crust, heating specific regions to tens of millions of degrees. Those localized flares create the hotspots astronomers now map in X-ray light. NASA's NICA and NUSTAR telescopes have made it possible to chart these features with precision. By watching how a magnetar's X-ray brightness changes as it rotates, researchers can identify patterns in the light curve. Brief pulses or dips that repeat each turn. These modulations reveal where the hotspots are and how they move. A single magnetar might have 2 or 3 primary hot zones, often located near its magnetic poles, but sometimes offset, drifting as the field evolves. Over time, those regions grow, cool, or migrate, hinting at the slow-motion rearrangement of the field beneath. The magnetar SGR 1935+2154 gave off X-rays and a fast radio burst in 2020, which shocked scientists by sending out a millisecond pulse that was so strong it could be seen from across the galaxy. Scientists looked at its X-ray data and saw clear hotspots flashing near the poles. These areas came and went as the magnetar turned, like bright countries on a world that was spinning. There were big changes in temperature between the spots, sometimes up to 10 million degrees. This suggested that cracks in the rock were letting energy out in different places. We had never seen the surface of a magnetar flex and crack under stress before. It was almost like seeing a live thing. To visualize what's happening, imagine the crust as a steel shell under continuous strain. The magnetic field below it twists like a coiled spring, storing energy for centuries. Eventually, the stress exceeds the crust's breaking point. It fractures. The release of tension sends waves of heat and radiation through the surface, igniting bright patches that fade only after days or weeks. Some of these events are mild, the stellar equivalent of a muscle spasm. Others are catastrophic, generating the giant flares that briefly outshine every other X-ray source in the galaxy. Now, though, the mapping gets really cool. But these hotspots do more than just show us where the crust broke. They also show us how the star's magnetic field changes over time. Simple bar magnets are steady dipoles, but magnetars are not. Their fields twist around each other, making toroidal parts that move energy between the two halves of the universe. Astronomers can follow that internal magnetic dance by keeping an eye on how hotspots move. If an area cools or goes away, it means that the field below it has loosened up or changed shape. When a new spot shows up somewhere else, it means that stress is building up in a different area. After years of watching, these maps turn into something like time-lapse pictures of how the magnets change over time. Some magnetars show hotspots that appear out of sync with their rotation. Instead of recurring every turn, they flicker at irregular intervals, hinting at processes deeper than the crust, perhaps superfluid vortex migration or magnetospheric reconnection events. These unpredictable flares remind researchers that the boundary between surface and interior isn't fixed. The magnetic field we see is only the visible part of a storm raging below. For instruments like NICER, observing these hotspots also improves our ability to measure the magnetar's size and shape. As the hot regions rotate in and out of view, relativistic light bending near the star's surface alters their apparent brightness. By modeling those distortions, astronomers can infer the curvature of space-time around the star, offering indirect evidence for general relativity in extreme conditions. In other words, every flare on a magnetar's surface doubles as a physics experiment. One nature runs for free 40,000 light-years away. Simulating the last microseconds. Before a neutron star like the Black Widow finally breaks apart, it doesn't happen slowly, it happens in microseconds. That quick change from star to black hole leaves no time for even light to adapt. In one instant, matter is a thick grid of neutrons. In the next, that structure is gone, crushed by gravity. There isn't a camera that can directly see this change, but computer models are starting to show what the last few seconds might be like. These aren't movie-like visuals. They're just physics models that have been pushed to their limits to try to show what happens when gravity, magnetism, and density stop working together. To simulate a neutron star's death, scientists must combine three kinds of physics that rarely cooperate: general relativity, quantum chromodynamics, and magnetohydrodynamics. Each describes a different layer of the catastrophe. General relativity handles gravity, how space-time warps as mass collapses. Quantum chromodynamics explains how neutrons behave when squeezed so tightly that their constituent quarks begin to merge. Magnetohydrodynamics governs the behavior of plasma and magnetic fields during the implosion. Bringing all three into a single code is like juggling lightning bolts while standing on quicksand. But over the past decade, supercomputers have finally made it possible. Teams at institutions like Los Alamos, Caltech, and the Max Planck Institute run these simulations on machines with tens of thousands of processors, solving billions of equations per second. They start with a virtual neutron star spinning at hundreds of rotations per second, containing around 2.3 solar masses of matter within a 20-kilometer sphere. Then they nudge it, adding a tiny bit of mass, simulating accretion, or letting rotation slow by a fraction of a percent. What follows is the closest thing we have to witnessing stellar suicide. At first, the outer crust vibrates, releasing seismic waves that race through the dense interior. The star compresses slightly and rebounds, but the rebound fails to overcome gravity. In less than a millisecond, the pressure at the core exceeds the nuclear degeneracy limit, and the neutrons themselves start to dissolve. The simulation shows the density curve rising like a wall, then flattening. That's the moment when quarks unbind, forming a transient quark-gluon plasma, a state of matter that hasn't naturally existed since the first microsecond after the Big Bang. The collapse then accelerates beyond all control. The star's magnetic field lines, twisted by rapid spin, snap and reconnect violently, ejecting bursts of plasma along the poles. This might explain the relativistic jets seen after some collapses, beams of material moving close to light speed. Within microseconds, the infalling matter reaches the Schwarzschild radius, the critical boundary where escape velocity equals the speed of light. The simulation stops here, not because the code can't continue, but because physics itself ceases to make sense. Inside the event horizon, space-time folds into a singularity, and no signal can return. The models tell us what will happen in the outside world, even though we can't see past that point. As the surface goes away, the gravitational potential changes so quickly that the space around it shakes. This is where the gravitational wave pulse we talked about earlier comes from. That wave, which only lasts milliseconds, tells us about the star's mass, spin, and symmetry, right up until it breaks apart. It's not just a death signal. It's the last bit of data from the fastest processor in the world. Simulations also reveal how clean the collapse is. In a supernova, much of a star's mass is blown outward in visible light and debris. In a pulsar collapse, nearly everything goes in. The efficiency is staggering. More than 99.99% of the star's material vanishes behind the event horizon. Only a paper-thin shell of plasma might escape, glowing for a few milliseconds as magnetic energy dissipates. To an external observer, it wouldn't look like an explosion. It would look like a fade-out. The pulses stop, the light dims, and the star is gone. One of the main questions these models try to answer is whether the collapse can make a short-lived object in the middle, which is sometimes known as a hypermassive quark star. If the pressure from quarks that aren't contained briefly equalizes gravity, the object might last for a few milliseconds before giving up. It would be revolutionary to find such a change in gravity waves. It would be proof that strange matter does exist. As of now, no measurement has proven it, but each new scenario makes the ideas about what that signal should look like even stronger. Pulsar death lines and radio silence. Every pulsar is only alive for a short time. As soon as it is born, when a huge star collapses, it starts to slow down. Every 100 years, it spins a little less rapidly. To make those amazing beams that blink across space like a cosmic lantern, the pulsar needs to be able to create energy between its magnetic poles. It drops, though, as the spin gets weaker. When it falls below a certain level, which scientists call the death line, the pulsar's radio speech stops working. Not a blast, not a flash, nothing but silence. This death doesn't mean the object ceases to exist. The neutron star remains, a cold, dense relic barely 20 kilometers wide, heavier than the sun and darker than coal, but without enough energy to accelerate charged particles and create pair cascades of electrons and positrons. Its magnetic field can't light up the radio sky anymore. The once vibrant beam fades into the cosmic noise. Astronomers sometimes call these objects radio ghosts, the dead pulsars that drift unseen, their spin too slow to sing. To understand the death line, imagine a graph where one axis measures rotation period and the other measures magnetic field strength. Active pulsars cluster in a region where those two values create enough electromagnetic potential to power their radio beams. The line separating them from silence is the boundary. Cross it, and you're out. The fastest spinners with weaker fields and the slower ones with immense fields can both survive a while. But as they age, spin down, and lose torque, they slide diagonally toward that graveyard. There's more than one death line, actually. Theoretical models propose entire death valleys and death bands, depending on what kind of emission mechanism a pulsar uses. Some rely on curvature radiation. Others depend on inverse Compton scattering or surface temperature to feed their magnetospheric plasma. That means there's no single cause of silence. It's a combination of physics and circumstance. A young pulsar might die early if its magnetic field decays faster than expected, while an older one might hang on for millions of years thanks to a residual field or a companion star feeding it fresh angular momentum. That's when things get compelling, because in paired systems, pulsars that are dead can sometimes come back to life. If matter from a close star hits the neutron star, it can spin the pulsar back up very quickly, making it what scientists call a millisecond pulsar. The rules of the graveyard are broken by these revived stars, which spin hundreds of times per second and send out radio waves again. They are a long way past the normal death lines, showing that the line isn't permanent. It's more like a sleeping curse than a final tomb. One of the key mysteries scientists are still chasing is why some pulsars shut down more abruptly than others. A few seem to flicker between on and off states, like cosmic light switches. These intermittent pulsars can go radio silent for weeks, months, or even years, then suddenly burst back to life with no clear trigger. Theories suggest changes in their magnetospheric current flow. Maybe the plasma density fluctuates, or the crust rearranges under magnetic stress. But so far, no model fully explains it. It's as if some pulsars stand right on the edge of the death line, wobbling back and forth like tightrope walkers between sound and silence. This mystery gets even deeper when we consider neutron stars that emit X-rays or gamma rays, but no radio waves at all. These radio-quiet pulsars may have already crossed the radio death line while still being active at higher energies. Their magnetic fields and surface temperatures let them glow through other processes. Thermal radiation, magnetospheric reconnection, or high-energy particle acceleration. NASA's Fermi telescope has found dozens of these silent screamers, invisible to radio telescopes but alive in the gamma-ray band. Fate of the feeding companion. Each Black Widow pulsar has a partner star that is doomed and stuck in an orbit so tight that it is slowly dying. The neutron star spins hundreds of times every second and constantly sends high-energy particles and radiation at its partner. That wind doesn't just heat the smaller star over time, it also wears it away atom by atom, like sanding a rock. The system nicknamed the Cannibal Pulsar, sometimes referred to by its designation PSR J0952-0607, offers a brutal case study. Its companion, once likely a regular main sequence star, has been whittled down to less than 1/20th the mass of the Sun. To the human eye, it would appear pitch black, barely glowing, its surface blasted and cracked by millisecond bursts of radiation. The pulsar feeds on it relentlessly, converting the stolen matter into rotational energy that keeps the neutron star spinning close to record speed. The irony is cosmic. The pulsar can't live without the companion, yet it's killing it. The accreted gas that once reignited its radio emissions now forms a tenuous plasma shroud around the binary, scattering radio waves and sometimes eclipsing them completely. Each orbit, lasting only a couple of hours, tightens as the companion loses mass and the system radiates gravitational energy. One day, the donor star will either evaporate entirely or shrink into a planet-sized core made of carbon and oxygen, essentially a diamond husk. Astronomers think we're watching that transformation in slow motion. Observations from optical telescopes show a faint heated hemisphere on the companion, the side facing the pulsar, while the far side remains dark and cold. It's the closest thing in reality to a two-faced world. one hemisphere ablaze, the other frozen. Over decades, as the pulsar's wind strengthens, that difference grows sharper. The process could end in 3 different ways: total evaporation, tidal detachment into a wandering fragment, or a catastrophic merger that reignites the neutron star's magnetosphere for the last time. If evaporation wins, the pulsar will end up completely alone, a solitary spinner with no more material to feed on, essentially a widowmaker that has consumed its mate. If merger occurs, though, all bets are off. The influx of matter could push the neutron star over the Tolman-Oppenheimer-Volkoff limit, the theoretical boundary between stability and collapse, exceed it, and gravity wins. The object would implode into a black hole, possibly producing a flash of gamma radiation strong enough to momentarily outshine an entire galaxy. That's why astronomers monitor these systems obsessively. They're natural laboratories for the extremes of physics: how matter behaves under degenerate pressure, how magnetic fields evolve near the quantum limit, and how close a neutron star can get to collapse without crossing it. In a sense, every particle the pulsar steals is a coin flipped against fate. One side survives, the other annihilation. Some Black Widow systems already seem to be nearing that point. Their spin periods are the fastest ever recorded, brushing against theoretical maximums where centrifugal force nearly tears the star apart. And yet, the feeding continues. The companion's slow death fuels the very rotation that could one day doom them both. It's a gravitational love story written in radiation and loss. Could a collapse reboot a jet? Each Black Widow pulsar has a partner star that is doomed and is dying slowly because it is stuck in a very tight circle. Every second, the neutron star spins hundreds of times and shoots high-energy particles and radiation at its buddy all the time. The wind doesn't just warm the smaller star over time, it also sands it away, atom by atom. Pulsars already act like miniature particle accelerators. Their magnetic poles funnel charged particles into narrow beams moving near light speed. But when the neutron star crosses its stability limit, the entire magnetic structure destabilizes. The collapse drags the magnetic field lines inward, winding them tighter than anything found elsewhere in the universe. Just before the horizon forms, that tension releases as a burst of magnetized plasma. It's the astrophysical equivalent of snapping a cosmic whip. Simulations suggest that for a few seconds, the collapsing magnetosphere could focus enormous energy into twin polar jets, not unlike the ones seen from supermassive black holes at galaxy centers. These would be smaller, shorter, and faster, blazing gamma-ray lances that could reach across thousands of light-years. If pointed toward Earth, they might appear as short gamma-ray bursts, the kind we've detected from random spots in the sky since the 1970s. Many of those mysterious bursts could be neutron stars undergoing their final transformation. If the collapse happens in a Black Widow system, where the pulsar has been feeding on a companion, the accretion disk around it might already be primed for ignition. When gravity takes over, that disk can briefly survive outside the newborn black hole's event horizon, swirling like a ring of superheated fire. The energy stored in that disk, magnetic, kinetic, and gravitational, could power a jet that lasts far longer than the collapse itself. The key is angular momentum. The faster the pulsar spins when it dies, the more rotational energy it can donate to its newborn black hole. Think of it like handing off a baton made of pure momentum. That transfer might produce a Kerr black hole, one of the fastest spinning types possible. And when that happens, the black hole's own rotation twists space-time around it, dragging magnetic field lines into an engine capable of launching a relativistic jet through a mechanism known as the Blanford-Znajek process. Why this object is watched constantly? Some celestial bodies make people curious. Others want to be watched. The pulsar called the Cannibal is definitely in the second group. As of years ago, NASA, the European Space Agency, and a number of university telescopes had their X-ray instruments trained on it. The reason is easy to understand. This pulsar lives in a dangerous area between being and not being. Every measurement taken from it feels like checking a heartbeat on borrowed time. Its spin rate hovers just below the theoretical limit before centrifugal force tears it apart. Its magnetic field strength, decaying yet still fierce, creates conditions right at the edge of stability. Astronomers track each tiny variation in its period because any sudden glitch or slowdown could signal that its neutron star structure is failing, an early whisper of gravitational collapse. Timing arrays like those in the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, monitor the cannibal pulsar to the microsecond. They use it not only as a test subject for extreme physics, but also as a probe for the fabric of space-time itself. A pulsar this stable, spinning hundreds of times per second, serves as a natural clock, one so precise it could detect passing gravitational waves. But with the cannibal, that precision comes with tension. Its consistency is uncanny, and that's exactly what makes researchers nervous. Each observation session begins with one question: will it still be the same today? A slight increase in rotational period might indicate a transfer of angular momentum, perhaps from an accretion event or a starquake shaking loose matter from its crust. On the other hand, a decrease might mean the pulsar has lost mass to radiation, pushing it closer to instability. It's a balancing act between two extremes, and so far, it's managed to stay upright on that cosmic tightrope. Optical and infrared telescopes, including the Very Large Telescope in Chile, watch the companion, the nearly evaporated star that still orbits it, because that's where early warning signs appear first. Changes in brightness, temperature, or orbital timing can reveal shifts in the pulsar's feeding behavior. The star's daylight side glows faintly from constant bombardment, while the night side remains invisible, a living thermometer of the pulsar's mood swings. The radio reports are even more telling. The Green Bank Telescope and FAST in China can see changes in the pulse strength of the beam. On some nights, it fades a little. In some cases, it stops altogether. These eclipses happen when the companion's gas escapes and forms clouds that block the radio signal for a short time. But there's also a darker possibility. The pulsar may be weakening, and its magnetic field may be changing to get ready for the final change. To catch that moment, researchers coordinate across continents. NASA's NICER module aboard the International Space Station checks for X-ray bursts. Fermi scans for gamma-ray spikes. Even gravitational wave observatories like LIGO are on alert, in case the system twitches hard enough to send ripples through space-time. It's a global stakeout for an event that could redefine what we know about compact objects. Because if this pulsar falls apart into a black hole, while it is still being watched, it will be the first time in history that people see the birth of a stellar mass black hole happen live. It would spin down, flare up, and then disappear, its beat stopping like a heartbeat that is about to stop. The information is very valuable. Equations about nuclear matter, magnetic decay, and quantum gravity would be written over and over again every second. Endgame scenarios and what comes next. In astronomy, every story has an ending, but most of the time the world doesn't give us a good one. There were several exciting ways that the cannibal pulsar story could end. What happens next rests on how well mass, spin, and magnetic decay are balanced. These are three forces that are constantly pulling against each other. The first and simplest ending is evaporation. The pulsar's companion, the last remnant of the original binary, could vanish completely. Each orbit strips away more gas until nothing remains but a faint trail of plasma. When that happens, the pulsar loses its fuel source. The radio beam will gradually dim, its spin will slow, and the once murderous star will slip beneath the death line, fading into radio silence. It would become what astronomers call a dead neutron star, a corpse that spins in darkness, detectable only through its gravitational pull. The second possibility is collapse. If the pulsar accumulates enough matter before its companion disappears, it could exceed the stability limit for neutron matter. At that instant, no known force can hold the structure together. Gravity wins, crushing neutrons into a singularity. Space around it warps violently, generating a burst of gamma radiation or even a short-lived jet. For a few heartbeats of cosmic time, the cannibal could outshine every other star in its galaxy, announcing its own death with light. Metamorphosis, a third bizarre result, has recently come up in theoretical talks. Some scientists think that when a neutron star gets very dense, it might not turn into a black hole, but into a quark star, which is a strange object made of loose quarks or strange matter. That would mean that the fall wouldn't fully work. Instead, the star would become stable again at a smaller radius, sending out a huge amount of energy and possibly starting its environment all over again. For binoculars, it would look like a star dying and then flaring back to life, which would be a false finish to a story about space. Whichever fate unfolds, the transition won't be quiet. Gravitational waves would ripple outward, carrying the story across the cosmos. Instruments like LIGO and Virgo could detect that tremor, while space-based observatories like LISA might pick up the low-frequency tail, proof that something once spinning fast had finally given in. For scientists, such a detection would be a once-in-a-generation event, allowing them to measure a neutron star's death in both light and gravity. If collapse is the final act, the aftermath will be eerie. A newly formed black hole would remain where the pulsar once was, perhaps orbited by the ghost of its companion or the ashes of an accretion disk. The system's radio signal would vanish instantly, replaced by silence. But the region around it might still glow for years in X-rays as the last bits of matter spiral inward. To astronomers, it would appear like a cosmic heartbeat that suddenly flatlined but left a lingering echo. Some simulations hint that the newborn black hole could retain a faint magnetic field, allowing it to power weak jets or flares for a short time. Eventually, even that will fade. What's left will be invisible, a gravitational shadow wandering the Milky Way, one of perhaps 100 million stellar black holes quietly drifting between stars. But wait, this silence doesn't mean the story is over. Every similar object in the sky is now a possibility, because the cannibal pulsar's change will teach us how these systems change over time. Another millisecond pulsar is near the end of its life somewhere out there. Another division is about to break apart. Another scientist is waiting for the beating to stop while they watch. And that's the story of the pulsar that just won't die. One heartbeat away from becoming a black hole, yet still spinning defiantly against time itself. If you made it this far, you're officially part of the few who understand how close we are to witnessing a real-time collapse. Hit like if you enjoyed diving into the science behind these cosmic predators, subscribe for more deep space mysteries every week, and watch the next video on your screen, where we explore more wonders of the universe.